eerily quiet compared to the active hearts of other galaxies. It occasionally flares with X-ray and radio emissions, subtle whispers of matter being consumed at its edge. This subdued activity makes it an ideal laboratory for testing Einstein's theory of general relativity in the extreme. Observations with radio telescopes, including the Event Horizon Telescope, have begun to pierce the veil around it, revealing a shadow-like ring, a silhouette cast by warped light bending around the event horizon. Surrounding this dark monolith is a region filled with turbulent gas, star formation, and enigmatic structures like the radio arc and the mysterious Fermi bubbles extending far above and below the galactic plane. These phenomena suggest that Sagittarius A** was not always so silent. In the past, it may have awakened in a storm of radiation, possibly shaping the environment of our galaxy on grand scales. Understanding the behavior of matter and light near Sagittarius A** doesn't just tell us about the Milky Way, it opens a window into the fundamental workings of the universe. Black holes stretch the fabric of spacetime, slow down time near their boundaries, and challenge the limits of physics. The closer we look, the more the ordinary laws of nature begin to falter. It is here, in this hidden core of our galaxy, that nature plays by rules we still struggle to fully comprehend. To peer into the realm of Sagittarius A** is to approach the very edge of what is physically possible. The black hole itself is surrounded by a region known as the event horizon, the point of no return, where gravity becomes so intense that not even light can escape. But this isn't just a boundary. It's a limit beyond which the known laws of physics dissolve into speculation. What lies beyond the horizon is unknown. A singularity? A bridge to another universe? Or something far stranger? Despite its invisibility, the influence of Sagittarius A** extends across thousands of light-years. Its gravity shepherds stars into tight orbits and may even help regulate the rate of star formation throughout the galaxy. As stars are pulled inward or disrupted, their material can be stretched and heated, creating spectacular bursts of radiation, brief but powerful echoes of cosmic consumption. Yet, these outbursts are rare. Sagittarius A** now appears to slumber, its feeding rate so low that it radiates less energy than a single household light bulb per unit mass. And yet, the quiet is deceptive. Evidence from surrounding structures hints at a violent past. The enormous Fermi bubbles, twin lobes of high-energy gas stretching tens of thousands of light-years, may be the fossil remains of an ancient outburst. Perhaps millions of years ago, Sagittarius A** blazed as a quasar, a beacon bright enough to outshine the rest of the galaxy. That light, long extinguished, may have rippled through the galactic medium, heating and shaping gas flows still visible today. More recently, astronomers have begun detecting ripples and flares from Sagittarius A** that arrive unpredictably, flashing in infrared or X-ray bands. These are likely caused by small clumps of matter, perhaps disrupted asteroids or wandering gas clouds, brushing too close to the event horizon. They spiral inward, heat up, and vanish. One such gas cloud, known as G2, was once thought to be on a collision course with the black hole, but it survived the encounter, a reminder of how much we still have to learn. The environment around Sagittarius A** is chaotic and extreme. Magnetic fields twist and tangle in invisible threads, and radiation bathes everything in energy. It's a place where stars are born and destroyed in rapid succession, where exotic objects like magnetars, neutron stars with ultra-strong magnetic fields, orbit perilously close to the brink of eternity. The interplay of forces here provides an unparalleled natural laboratory, offering astronomers the chance to witness physics pushed to its breaking point. Yet for all its darkness, Sagittarius A** may also play a role in galactic balance. Some theories suggest that supermassive black holes help to regulate their host galaxies, emitting enough energy during active periods to prevent runaway star formation and recycle material. In this way, the black hole at the center becomes both destroyer and creator, a paradox at the core of the Milky Way. As telescopes become more powerful and algorithms more precise, we are finally beginning to map the turbulent, crowded neighborhood of Sagittarius A** in exquisite detail. The stars that orbit near the black hole, often referred to as the S-star cluster, are like clock hands sweeping through spacetime. Each of their paths is subtly altered by relativistic effects, their orbits precess, their clocks tick more slowly, and their light bends as it climbs out of the warped gravitational well. These motions have allowed scientists not only to confirm the existence of a supermassive black hole, but to test general relativity with unprecedented accuracy, and so far, Einstein's predictions have held firm. Yet there is still much we cannot see. Some simulations suggest that smaller black holes, remnants of ancient stars, may swarm invisibly around Sagittarius A*, forming a dark halo that distorts the motion of stars and gas. These stellar corpses, spiraling in toward the supermassive center, could occasionally collide or merge, sending out gravitational waves rippling across the galaxy. We cannot detect them directly, not yet, but future observatories like LISA, Laser Interferometer Space Antenna, may be able to eavesdrop on these ghostly conversations between dead stars and the dark heart of the Milky Way. And then there's the matter of time itself. Near Sagittarius A*, time moves differently. An observer falling toward the event horizon would, in theory, appear to freeze from an outside perspective, forever suspended at the edge. But for the falling object, time continues normally, until it reaches a place where physics loses all meaning. This duality, where time stretches and bends depending on your point of view, isn't just poetic. It reveals something fundamental about the nature of reality, and how black holes might serve as windows into the very structure of the universe. Some researchers have begun to speculate that the information swallowed by a black hole may not be lost forever, as once thought. The so-called information paradox, one of the greatest unsolved problems in physics, suggests that our understanding of quantum mechanics and gravity may be incomplete. Could Sagittarius A** hold clues to a deeper theory, one that unites the macroscopic laws of general relativity with the microscopic rules of quantum physics? If so, the key may lie not in what we see, but in what remains forever hidden. Meanwhile, the black hole continues its silent reign. It does not glow, it does not move, and yet everything near it responds to its presence. It is a singularity, not only in space, but in mystery. A gravitational monarch ruling a kingdom of stars, whose throne lies buried beneath veils of dust and the whispers of ancient light. It is not merely the center of our galaxy. It is a portal to the edge of human understanding. From Earth, we can never observe Sagittarius A** directly with visible light. The galactic center is obscured by immense clouds of interstellar dust. But with radio, infrared, and X-ray observatories, we can peel back these veils and glimpse the invisible. Instruments like the Very Large Telescope, VLT, the Chandra X-ray Observatory, and the Atacama Large Millimeter/Submillimeter Array, ALMA, all converged their vision on this hidden titan. Their findings are astonishing: a maelstrom of plasma and magnetic fields, a region of gravitational shear and relativistic speeds, and light itself, bent into rings and arcs as it tries to escape. The Event Horizon Telescope's image of Sagittarius A*, released in 2022, was a milestone in this journey. Though blurry, it offered the first direct evidence of the shadow of the black hole, encircled by a glowing halo of hot gas swirling at nearly the speed of light. This shadow is not a simple absence of light, but a gravitational imprint, a signature of spacetime twisted into a vortex. The ring we see isn't the black hole itself, but the last orbit light can make before being swallowed. It is both a boundary and a symbol, a fiery crown for an invisible monarch. And what lies beyond the visible and theoretical borders of Sagittarius A*? Some physicists wonder if black holes like this are connected to the fabric of the wider universe in unexpected ways. Could the center of our galaxy also be the mouth of a wormhole, a conduit to another part of space, or another cosmos entirely? While such ideas remain speculative, they drive a bold frontier of physics where mathematics dares to describe what observation cannot yet confirm. The galactic center is also a crucible of extremes. Temperatures soar to millions of degrees. Gravity is strong enough to twist the orbits of entire star clusters. Particles accelerate to near-light speed in jets and flows, possibly spawning exotic high-energy phenomena. Somewhere within this chaos, dark matter may lurk, shaping the orbits of stars and influencing the motion of gas with its unseen hand. The very environment around Sagittarius A** may be a testing ground for understanding the dark scaffolding that binds the universe together. But beyond science, there is something deeply mythic in this region of space. Ancient civilizations may not have known what lay at the heart of the Milky Way, but they understood that the sky had a center, a place where stars thickened and mysteries dwelled. Today, with all our instruments and equations, we still stand at the edge of that unknowable center. We name it, model it, photograph its shadow, yet it remains a frontier not only of physics, but of wonder. Sagittarius A** is not just the center of our galaxy. It is the anchor point of a billion stars, the invisible axis around which the Milky Way spins. And in a deeper sense, it is a mirror, reflecting the limits of our understanding, the depth of our curiosity, and the immense journey that still lies ahead. As we delve further into the mysteries of Sagittarius A*, we are not just learning about a single black hole, we are uncovering the history, structure, and fate of the Milky Way itself. The stars that orbit near the galactic center are ancient, many of them formed during the galaxy's early epochs. They carry with them the chemical signatures of past generations, encoded like genetic memories in their light. Studying these stars helps astronomers reconstruct the story of our galaxy's formation, its violent mergers, its periods of rapid star birth and quiescence, and the central role the black hole may have played in shaping all of it. In recent years, a remarkable discovery added a new layer to this story, a compact cluster of young, massive stars, the so-called paradox of youth. These stars, known as the S-stars, orbit astonishingly close to Sagittarius A*, in a region where intense gravitational tides should prevent any gas from settling and forming new suns. And yet, here they are, hot, bright, and impossibly close to the abyss. How did they form? Did they migrate inward after forming farther out, or could they have emerged from the wreckage of a larger disrupted system? Their very existence is a cosmic riddle that continues to challenge astrophysical models. Some researchers speculate that the core of the Milky Way may host not just one black hole, but multiple compact objects, perhaps remnants of past collisions, hidden among the glare of stars and gas. Others wonder whether Sagittarius A** will one day become active again, igniting into a quasar that floods the galaxy with radiation. If a large enough gas cloud falls into its grasp, the black hole could awaken from its current slumber, feeding voraciously and reshaping the surrounding environment in a cosmic storm of light and energy. And while such an event might sound distant, its effects could echo far across the galaxy. The radiation from an active Sagittarius A** would not reach Earth directly. We are safely nestled about 26,000 light-years away, but it could impact the broader ecosystem of the Milky Way. High-energy particles, magnetic storms, and large-scale gas flows could influence star formation, rearrange interstellar matter, and alter the very structure of the galactic disk. Even now, some of the radiation emitted by the black hole, past or present, may be echoing back toward us after reflecting off distant clouds. These light echoes allow astronomers to reconstruct past activity, like forensic traces of a crime scene billions of years old. Each echo is a flicker from the past, a brief glimpse into the times when Sagittarius A** may have roared instead of whispered. And perhaps most profoundly, Sagittarius A** reminds us that every galaxy, no matter how vast and luminous, holds a secret heart of darkness. These invisible engines of gravity shape the cosmos from the inside out. They are born in the death throes of stars, grow through mergers and accretion, and eventually become the silent architects of structure on galactic scales. From the outside, a galaxy appears as a glowing spiral or an elliptical haze, but at its core lies something that defies sight, defies understanding, and redefines what it means for something to exist. Sagittarius A** is more than a black hole. It is a cosmic paradox, a nothingness with mass, a void that defines motion, a shadow that holds together a galaxy of light. And as our instruments improve and our theories evolve, we inch ever closer to the event horizon, not just of a distant object, but of knowledge itself. And as we drift closer to that horizon of understanding, we begin to realize that Sagittarius A** is not merely a destination for scientific inquiry, it is a threshold. A boundary where the familiar breaks down, and something deeper waits. Every photon we detect, every orbit we measure, every flare we track, is a message from the edge of what we can know. And yet, these messages are distorted, delayed, stretched by gravity and time. They are signals from a realm where the universe folds inward, where time is no longer linear and space is no longer flat. What we study near Sagittarius A** challenges not only physics but philosophy. It forces us to confront questions once confined to myth and metaphysics. What happens at the end of time? Can something fall forever? Does the information of the universe ever truly vanish? These aren't just abstract curiosities. They are the scaffolding of existence, the rules that decide how stars live and die, how galaxies evolve, and possibly, how the universe itself will end. In this context, Sagittarius A** becomes a cosmic oracle. It speaks through equations and emissions, through the precession of orbits and the silence of light that never returns. And we, perched on a rocky planet in the galactic suburbs, are listening. We build machines to extend our senses, machines that hover in the Chilean desert, float in orbit above Earth, or stretch across continents in synchronized precision, all focused on a single, silent point in the night sky. Even now, new missions are being imagined that will explore this gravitational cathedral in more detail than ever before. Future X-ray interferometers, gravitational wave observatories, and radio arrays on the moon may one day bring us images so clear that the chaos at the event horizon will become legible. We may see matter spiral inward in real time, watch magnetic fields twist into jets, or witness the moment a star is torn apart and consumed. These are not just scientific dreams. They are blueprints for encounters with the deepest architecture of reality. And what if, in observing Sagittarius A*, we are also observing something about ourselves? The black hole is a mirror of extremes: absolute gravity, ultimate silence, perfect darkness. But it also holds a strange beauty, the way light bends around it into luminous rings, the elegance of stars that orbit invisibly drawn to a point, the delicate balance of chaos and order in a place where all should collapse. It reminds us that even in the universe's most violent and enigmatic corners, there is structure, rhythm, and astonishing coherence. In the end, Sagittarius A* is not a threat, nor a monster, nor a hole in the galaxy. It is a process. A cosmic function. A reminder that the universe is not static, but evolving, folding, devouring, and creating in one breathless, endless cycle. And in that dark center, that beating heart of shadow, we find not just the gravitational axis of our galaxy, but perhaps a symbol of something far more profound, that the greatest truths may lie in what we cannot see, and the most powerful forces in what does not emit light. To gaze into the realm of Sagittarius A* is to look not only across space, but backward through time. Every photon that reaches our instruments has traveled for tens of thousands of years, carrying with it a story written in warped spacetime and filtered through cosmic dust. The light we gather today began its journey when early humans painted on cave walls, long before the first cities rose, before we had a name for stars. And yet, that ancient light brings us face to face with the future of astrophysics, with questions that lie beyond the limits of our current theories. We stand now on the precipice of an era in which black holes may no longer be distant enigmas, but laboratories of the fundamental. Scientists envision not only observing Sagittarius A*, but using it as a natural particle accelerator, as a lens, as a proving ground for quantum gravity, the long-sought theory that will unite the smooth geometry of general relativity with the granular randomness of the quantum world. Some models even suggest that the information encoded in particles falling into Sagittarius A** may be smeared across its event horizon, preserved holographically, waiting to be decoded. It's as if the black hole itself is a kind of cosmic archive, not one we can easily read, but one that may one day reveal how reality encodes itself. Theoretical physicists speak of black hole entropy, of Hawking radiation, of firewall paradoxes and entanglement across horizons. These ideas are no longer science fiction, they are active, ongoing attempts to grasp the logic that binds the cosmos together at its most extreme. And Sagittarius A*, our own private singularity, is the nearest stage on which this epic drama plays out. The mystery is layered. There are stellar black holes, the remnants of dead stars. There are intermediate mass black holes, elusive and hard to confirm. And there are giants like Sagittarius A*, millions of solar masses packed into a point smaller than Mercury's orbit. But how did it form? Did it grow from a single ancient seed black hole? Was it fed by collapsing star clusters, by gas flows from the galaxy's spiral arms, by tidal captures of unlucky stars? Or was it always there, primordial, older than the galaxy itself? We don't yet know. But what we do know is that without Sagittarius A*, our galaxy would be incomplete. It provides gravitational cohesion, dynamic structure, and a kind of deep time clock at the center of everything. Even the spiral arms of the Milky Way, their graceful curves, their star-forming ridges, their intricate dust lanes, may have been influenced by the presence of this silent anchor. Like the heart within a living organism, it pulses invisibly, its rhythm slow, but its presence vital. As we continue to study it, we are reminded that our position in the galaxy is both peripheral and privileged. We are far enough to be safe from its violent reach, but close enough to observe its every flicker. We orbit in the galactic suburbs, but our minds reach toward the core. And in that reaching, something ancient awakens, a desire to understand not just the mechanics of the universe, but the meaning of darkness, of depth, of the unknown. Sagittarius A* is not a conclusion. It is an invitation to explore what happens when matter meets the infinite, to question the permanence of information, to imagine what spacetime looks like when bent to its breaking point, and to accept that, sometimes, the most profound truths are whispered from the places where light cannot go. And so we listen, not with ears, but with arrays of telescopes linked across continents, with detectors tuned to the faintest ripples in spacetime, with algorithms trained to decode silence. Each observation brings us closer, pixel by pixel, to that gravitational abyss at the center of our galaxy. Yet the closer we get, the more the universe resists clarity. The image sharpens, but the questions multiply. Why is Sagittarius A** so quiet now, after possibly raging in the past? What is the nature of the material that orbits so close, just above the event horizon? Could quantum effects, hidden from us now, one day reveal that black holes are not the end of information, but its metamorphosis, a transition from one form of reality to another? Some theories propose that black holes, rather than being destructive endpoints, are phases in a cosmic cycle. That within them, time and space invert. That perhaps what collapses here may expand elsewhere. Others suggest that black holes could be encoded with the seeds of future universes, that what disappears beyond the veil of Sagittarius A** might be reborn in a different cosmic domain. Such ideas are speculative, yes, but they arise naturally from the equations that govern black holes and the fabric of spacetime. Meanwhile, in the surrounding region, the central molecular zone, immense clouds of gas swirl chaotically, dense and cold and heavy with potential. Here, stars are born at accelerated rates, huddled in clusters, their lives brief but brilliant. Some of these stars will end as supernovae, scattering metals into the galactic core. Others will become neutron stars, white dwarfs, or even fall into the very black hole they once orbited. In this way, the region around Sagittarius A** is not just a gravitational center, it is a crucible of transformation, where matter, energy, and time are kneaded together into new forms. The dance is ongoing. Every day, somewhere near the center, a star completes another revolution. A wisp of gas falls inward. A flare flashes and fades. And all of it is connected, to us, to the stars we see at night, to the long spiraling arms that stretch across the sky. We orbit this black hole once every 230 million years. The last time Earth was in this position around the galactic center, dinosaurs ruled the continents. In the next galactic year, who, or what, will be watching? Sagittarius A** is the beginning of such thoughts. It humbles our timelines, our distances, our certainties. It sits at the dark center of the Milky Way not as a monster, but as a monument, to gravity, to time, to the unseen forces that sculpt reality. It is not a void. It is the forge of light. And though it hides in darkness, it holds the very key to understanding what the universe is, and what we might become. And still, the questions deepen. In the years to come, our tools will sharpen. Projects like the Next Generation Event Horizon Telescope, more sensitive and finely tuned, promise clearer glimpses of Sagittarius A*, images that may resolve the turbulence of plasma orbiting at relativistic speeds, or even track hotspots of matter as they whip around the event horizon. These bright knots, possibly magnetic reconnection events or fragments of disrupted bodies, may orbit so rapidly that their motion becomes visible over the course of a single night. Watching them move would not only be a feat of observation, but a direct experience of warped time and curved space. Meanwhile, instruments like the gravity interferometer in Chile have already begun to detect subtle effects that were once purely theoretical: gravitational redshifts, time dilation, orbital precession. Each of these is a thread in a larger tapestry, revealing that the spacetime around Sagittarius A** is not a backdrop, it is alive, dynamic, responsive to the presence of energy and mass. Yet even more haunting than what we can observe is what remains concealed. Deep inside the event horizon, spacetime folds so tightly that our mathematics breaks. The singularity, a point of infinite density, is not just a failure of our equations, but perhaps a signpost. Something is missing. Some deeper law, some more elegant framework, must lie beyond. And so we press against the boundary of knowledge, one photon at a time, hoping for a glimpse of what lies beyond infinity. But even if we never see inside, Sagittarius A** continues to shape us. It influences how we model the birth of galaxies, the role of black holes in cosmic evolution, the entropy of spacetime itself. It challenges us to consider time not as linear, but malleable, a river that can stretch, slow, and whirlpool around massive bodies. It invites us to reimagine the meaning of distance and causality, of presence and absence. In the vicinity of a black hole, light can circle endlessly, time can fracture, and cause can follow effect in strange, looping geometries. It reminds us that space is not empty. That darkness is not silence. That the most powerful engines in the cosmos are not the ones that shine, but the ones that consume. And perhaps most profoundly, it unites the infinite and the intimate. For even as we study Sagittarius A** as a distant colossus, we come to realize it is also part of us. The atoms in our bodies were forged in stars whose orbits it governed. The dust in our lungs once passed through the arms of a galaxy shaped by its pull. The rhythm of our planet, its revolutions and tides and seasons, unfolds within a galaxy that spins, ever so slowly, around that invisible core. So when we look up into the night sky and trace the faint arch of the Milky Way, we are not just gazing at stars. We are seeing the great wheel of our home, turning around a center we cannot see, but which sees us, pulls us, holds us. And in that center, in that gravitational heart of our galaxy, the silence is not empty. It is waiting. It is watching. It is the shadow behind the light, and the beginning of all understanding. There will come a time, perhaps sooner than we expect, when humanity reaches farther than ever before. When robotic probes drift into the depths of the outer solar system and beyond, when telescopes on the moon or orbiting the Earth in gravitationally pristine silence peer deeper into the cosmic abyss. And when that time comes, Sagittarius A** will still be there. It will still be watching. Silent. Steady. Ancient beyond reckoning. Our instruments will grow more refined, our theories more daring, and yet the heart of the galaxy will remain a place of riddles carved in gravity and shadow. Some imagine that one day, intelligent life, perhaps even our distant descendants, might travel toward that center. What would it mean to approach the black hole not as observers from afar, but as travelers of curved spacetime? Could technologies emerge that allow us to hover near the event horizon, to sample the extremes without falling in? Would we listen to the hum of radiation as it spirals inward, feel the stretching of time, the smearing of space? Would we begin to decode the very structure of reality not from afar, but from within? Or perhaps Sagittarius A** is not meant to be touched. Perhaps it is a monument to limits. A reminder that there are places in the universe where light itself ends, where knowledge halts at an asymptote, where presence is replaced by inference. And yet, it is precisely this resistance, this refusal to yield its secrets easily, that draws us closer. Because the human mind is restless. We do not fear the darkness. We study it. We name it. We model it in simulations, recreate it in particle colliders, challenge it in equations chalked on blackboards and calculated on supercomputers. And slowly, year by year, flare by flare, we are beginning to understand. Sagittarius A** is not a void at all. It is a structure. A lens. A crucible. A processor of matter and energy and time. It is a boundary between what is and what could be, a gate between this universe and every theory that dares to imagine beyond it. It is an artifact of the Big Bang, a consequence of cosmic evolution, and a sculptor of galactic futures. The Milky Way spirals. Stars are born. Others die. Gas flows. Radiation pulses. And through it all, at the exact gravitational center, Sagittarius A** remains unmoved. It anchors the galaxy like a keel anchors a ship, invisible but indispensable. Everything orbits it. Everything is drawn toward it. And yet, everything is also repelled, kept just far enough to continue dancing, not falling. Perhaps that is the truest metaphor for knowledge itself. We are pulled inward, always closer, never arriving. Each revelation opens onto deeper mysteries. Each solution leads to new paradoxes. And in that endless pursuit, in that fearless spiral toward the center of all things, we become something more than a species. We become a question, launched toward the dark. And the answer, silent, immense, still waits in the place where light bows to gravity, where time loops into stillness, where the galaxy holds its breath, in the black and beating heart of Sagittarius A star. And so we orbit, not just physically, but intellectually, spiritually, mythically, around this singular point where the known dissolves into the unknowable. Sagittarius A** has become more than an astrophysical object, it is a symbol. A gravitational Rosetta Stone, etched not with hieroglyphs but with distortions of spacetime, flares of radiation, and a ceaseless whirl of stellar trajectories. It is the cathedral of gravity, and every photon that bends in its presence is a whispered verse from the book of the cosmos. There is a strange poetry to this place, that in a universe governed by light, by the speed at which it travels and the images it paints, the most important object in our galaxy is one that emits none. And yet, its silence is louder than any star's roar. The absence of light is its signature. The void is its presence. It doesn't need to shine to be seen. It doesn't need to speak to be heard. It shapes everything without a sound, like memory, like time, like fate. In dreams and metaphors, ancient cultures told stories of underworlds, of gods that dwell in darkness, of chasms where souls pass and never return. Today we speak not of myth but of mass and energy, of curvature and event horizons, and yet, in Sagittarius A*, the resonance remains. We've given it a designation, a catalog number, a celestial coordinate. But we might as well call it what it truly is, the heart of mystery. And still, it pulses. Not like a star, not with light, but with gravity. It hums in the background of our understanding, distorting time, guiding matter, bending the very geometry of existence. Around it whirl the remains of stellar generations, gas clouds glowing with infrared heat, filaments of radio energy, X-ray flashes from fallen stars. Each orbit is a confession. Each flare a flare of remembrance. Something happened here. Something still happens. We cannot touch it, but we are touched by it. Perhaps one day, we will learn to read the signals hidden in its flares, the chaotic whispers of magnetic fields and torn plasma. Perhaps we will develop a unified theory of quantum gravity, born from the paradoxes it embodies. Perhaps Sagittarius A** will become, not the end of knowledge, but its rebirth, the place where the old laws die and a new physics begins. The singularity not as a wall, but a threshold. And even if we never cross it, even if it remains forever veiled by the event horizon, we will continue to trace its silhouette. Because the darkness it embodies is not emptiness. It is possibility. So we look up. Not with fear, but with reverence. Not with finality, but with longing. Not because we expect an answer, but because we are the kind of beings who must ask the question. What lies at the heart of everything? What endures when light fails? What truths are revealed only in the silence? There, in the center of our galaxy, wrapped in invisible fire and curved spacetime, the question still turns. And Sagittarius A** waits. It waits, not passively, not inertly, but with a presence that reshapes everything around it. It does not need motion to act, nor light to declare its influence. Its very stillness is dynamic, its silence the loudest sound in the galactic symphony. Time near Sagittarius A** slows to a crawl, while space itself curves like a bow under tension. And across tens of thousands of light years, that tension is felt. Even here, in our distant stellar neighborhood, its gravity plays a quiet part in our orbit through the galaxy. We drift not freely, but along a trajectory defined in part by this invisible anchor. The sun, the planets, our pale blue dot, all are part of a larger structure, a spiral bound by that central weight. Life evolved in that context. Our calendars, our tides, even the length of our days, are all chapters in a greater story whose author sits silent at the center. And so, from a speck of matter orbiting a middling star in a far-off spiral arm, we dared to ask, what lies at the center? To even pose that question is an act of defiance. Of imagination. Of cosmic intimacy. For we are made of the same material that once flowed toward that dark heart, atoms forged in supernovae, shaped by galactic tides, lifted by stellar winds. The iron in our blood may have passed through clouds stirred by the ancient activity of Sagittarius A star. The calcium in our bones may have once been part of a star that danced close to the brink and flared in a last cry before vanishing. We do not just study the black hole. In some profound way, we remember it. And as we continue to probe its edge, we also chart the edge of what it means to be observers in this universe. Sagittarius A** challenges the sharp lines we once drew, between light and darkness, between past and future, between here and there. Near it, space twists into spirals, time loops upon itself, and causality trembles at the edge of the abyss. It reveals that even the most fundamental assumptions, that events have an order, that information moves one way, that things can be known, may fracture at the center of a galaxy. But there's beauty in this uncertainty. In knowing that not everything can be predicted. That the cosmos still holds places where the map fades into shadow, where knowledge becomes art, where physics becomes poetry. Perhaps that is the true gift of Sagittarius A*, not answers, but inspiration. Not clarity, but awe. It reminds us that the universe is not merely a machine to be solved, but a cathedral to be entered with humility. And though we may never walk its inner corridors, we orbit its silence with reverence, drawing nearer not in distance, but in understanding. So we continue to build our instruments, to refine our equations, to gaze deeper into the void, not to conquer it, but to witness it. To listen. To learn. And to honor the mystery that sits unmoving, unseen, and eternal at the center of us all. And as our journey circles ever inward, through data, through theory, through the endless questions we cast like threads into the dark, we come to recognize that Sagittarius A** is not only a physical entity, but a mirror. In it, we see the structure of the cosmos, yes, but also the structure of ourselves. Our need to understand, our thirst for meaning, our willingness to peer into the unknowable, all of it reflects back at us from that abyss. For in the end, we are not so unlike the photons that spiral near the event horizon. We travel great distances in the search for clarity, we orbit ideas we cannot yet grasp, and we are bent, like light itself, by forces greater than ourselves, gravity, time, wonder. And the deeper we look into Sagittarius A*, the more it becomes a meditation on boundaries. The boundary between matter and nothingness. Between time and timelessness. Between the visible and the veiled. It is the horizon beyond which there is no return, and yet we return to it again and again, with sharper eyes, better instruments, deeper questions. And someday, maybe, we will begin to understand not just what it is, but why it compels us so profoundly. Why a featureless void at the center of a galaxy stirs such hunger in the human mind. Why a silent gravitational shadow can echo louder than a supernova. Why a place that hides everything is where we go to seek the ultimate truth. Perhaps it is because, in Sagittarius A*, we find a pure expression of nature's paradoxes, that the strongest force is the one we cannot touch, that the brightest insights emerge from the darkest places, that to lose everything, even light, is not necessarily the end, but another beginning. Because what Sagittarius A** teaches us, with every flare, every orbit, every distortion of spacetime, is that the universe is not only governed by rules, but by stories. And the story of this black hole is also the story of gravity itself, how it gathers, how it shapes, how it transforms silence into structure and nothingness into power. So when we speak of Sagittarius A*, we are not speaking only of science. We are speaking of myth made real. Of darkness that bends reality. Of a truth so vast, so strange, so beautiful, that it must be approached like a poem, read in fragments, interpreted through wonder, and never fully finished. And still it waits. At the crossroads of light and shadow. At the spine of our galaxy. At the very place where knowledge ends and imagination begins. Sagittarius A star. Not a destination. But a calling. A calling that hums through the spiral arms of the Milky Way like a deep, inaudible chord, ancient, constant, gravitational. It is there in the way stars cluster more tightly toward the center, in the gentle warp of the galactic disk, in the faint ripples of gas and dust that pulse outward like echoes from a forgotten drum. Even the structure of our galaxy, the elegant bar that runs through its core, the winding arms that sweep around like the petals of a cosmic flower, all are, in some way, expressions of that central mass, that hidden presence that never speaks, but commands. And what do we do with that calling? We answer, as we always have. With questions. With equations. With wonder. We answer by building observatories on mountaintops, launching satellites beyond the pull of Earth, linking telescopes across oceans to form a planet-sized eye. We teach machines to listen, to watch, to reconstruct the chaos into order, to read the light that brushes the edge of the abyss and tell us what it saw. We filter the noise, sharpen the signal, and in doing so, draw the silhouette of the unimaginable. In that silhouette, that blurred, golden ring revealed by the Event Horizon Telescope, we saw something more than confirmation. We saw a glimpse of the universe's architecture. A fingerprint of curved spacetime. A hole in the fabric of reality itself, bordered not by walls, but by warped light completing its final orbit. And though that image was a triumph of science, it also felt like a message. As if the cosmos itself had opened one dark eye and said, I am still here. Come closer. And so we will. Not just through instruments and theories, but through imagination. Sagittarius A** has become a kind of cosmic axis mundi, the point around which our collective dreaming turns. It is the heart of maps we cannot finish, the end of paths we cannot walk, the question mark stamped in the middle of our sky. For all our satellites, our mathematics, our simulations, we are still just explorers. Still huddled around the firelight of our stars, gazing into the dark woods beyond. And in that darkness, Sagittarius A** is the ancient tree we cannot climb, but cannot ignore, the black monolith in the clearing of the galaxy. We may never touch it. We may never know what lies beyond its event horizon. But its gravity, literal and metaphorical, pulls us nonetheless. It draws our thoughts, our dreams, our aspirations. It reshapes not just matter, but meaning. Because in the end, what is Sagittarius A** if not a reminder? That the universe is larger than our understanding. That beauty can live in silence. That mystery is not a problem to be solved, but a truth to be honored. And as we drift onward, planet, star, civilization, turning around that silent center, we carry its presence within us. A darkness that anchors light. A question that gives shape to thought. A gravitational hymn sung in the key of awe. Sagittarius A**, the silent sentinel at the heart of the galaxy, and the echoing heart of every being who dares to ask why. And so, the story does not end, it deepens. For as long as the Milky Way turns, as long as stars are born and worlds awaken, Sagittarius A** will remain, unmoving, unseen, yet central to everything. It will continue to shape the paths of stars, to bend time into spirals, to whisper across the void in the language of gravity. It will outlive empires, planets, even the sun itself. Long after our species is gone, after our cities have crumbled and our voices have faded into cosmic background noise, the black hole will still be there, watching, waiting, holding the memory of a galaxy. And perhaps, far in the future, new minds will arise, forged in other corners of the Milky Way or born under alien stars, and they, too, will look toward the center. They will trace the same spiral path of curiosity. They will feel the same pull toward the unknown. And they will find it, that dark, silent core where space collapses and time becomes strange. And they, too, will listen. Because Sagittarius A** is not merely a place in space. It is a question written in gravity. A riddle etched into the structure of the cosmos. A reminder that even in darkness, there is order. Even in silence, meaning. Even in the void, a center. And in that center, unseen but undeniable, the galaxy turns. And we, for a brief, bright moment, are part of the dance. Dark matter is one of the most elusive and perplexing concepts in contemporary astrophysics, a form of matter that neither emits nor absorbs light, rendering it effectively invisible to conventional observational methods. Yet, despite its mysterious and intangible nature, dark matter constitutes a staggering 85% of all matter in the universe, profoundly shaping the cosmic structures we observe. The first hints of dark matter emerged in the 1930s when astronomer Fritz Zwicky studied galaxy clusters. He noticed a strange discrepancy. The galaxies within these clusters were moving at velocities much higher than those predicted by the visible matter alone. If only luminous mass were present, gravity would not be strong enough to prevent these clusters from dispersing. Zwicky concluded that some unseen dunkle materie, or dark matter, was holding these massive structures together. Decades later, astronomer Vera Rubin reinforced this theory with her observations of galaxy rotation curves. Rubin and her colleagues found that stars in spiral galaxies moved at nearly constant speeds, regardless of their distance from the galactic center. This contradicted predictions based solely on visible matter, where stars farther from the center should orbit more slowly. The only explanation was the presence of a massive, invisible halo of dark matter enveloping galaxies, providing the gravitational glue necessary to maintain their structural integrity. But what exactly constitutes dark matter remains an open and tantalizing question. Physicists propose several candidate particles to explain this invisible substance. Among the most prominent theories are weakly interacting massive particles, WIMPs, hypothetical particles that interact with ordinary matter only via gravity and the weak nuclear force, making their detection exceedingly challenging. Another intriguing candidate is axions, extremely light and weakly interacting particles theorized to resolve problems in quantum chromodynamics. Alternatively, massive astrophysical compact halo objects, MACHOs, dense objects such as black holes, neutron stars, or faint white dwarfs, were once considered as dark matter candidates, though extensive searches have largely ruled them out as the primary constituents. Observational techniques have significantly advanced, yet direct detection of dark matter remains elusive. Current experiments involve detectors placed deep underground, shielded from cosmic rays, searching for rare interactions between dark matter particles and ordinary atomic nuclei. Observatories in space also investigate indirect signs, looking for excess gamma rays, neutrinos, or cosmic rays that might result from dark matter particle annihilations. Yet, despite rigorous experimental efforts, dark matter has so far evaded direct confirmation, leaving astrophysicists and cosmologists navigating in the realm of theoretical inference and indirect observation. Dark matter's influence is not limited to galaxies and clusters alone. On cosmic scales, it shapes the large-scale structure of the universe itself. In the early universe, slight density fluctuations in dark matter served as gravitational wells, attracting ordinary matter and eventually leading to the formation of galaxies, stars, and planetary systems. Without dark matter, simulations indicate that the universe would lack the complex filamentary structures observed today, galaxies would never coalesce, stars would fail to form, and life itself might never arise. Moreover, gravitational lensing, the bending of light by massive objects, provides another crucial observational signature. Observations of distorted and magnified images of distant galaxies and quasars have consistently demonstrated more mass in galaxy clusters than visible matter alone can account for. This excess gravitational effect provides compelling indirect evidence for dark matter's pervasive presence. Cosmological observations, notably measurements of the cosmic microwave background radiation by satellites such as Planck and WMAP, independently confirm dark matter's essential role. These precise observations indicate that ordinary matter comprises only about 5% of the total energy content of the universe, with dark matter making up around 27%, and the mysterious dark energy accounting for the remaining 68%. This consistent agreement across independent observational methods strengthens the argument for dark matter's reality and necessity. In sum, dark matter is indispensable, holding cosmic structures together, shaping the formation of galaxies, and influencing the very evolution of the universe. Its nature remains one of modern science's greatest mysteries, fueling extensive research across multiple scientific disciplines. The existence of dark matter highlights a profound truth: the visible universe we observe and understand is but a small fraction of the cosmic tapestry. A vast portion remains invisible, detectable only through its gravitational influence on the matter we see. The scientific quest to identify and understand this enigmatic component continues to push the boundaries of physics, cosmology, and our understanding of the universe. In recent years, astrophysical simulations have become increasingly sophisticated, attempting to replicate the universe's evolution by incorporating different scenarios and properties of dark matter. Such simulations have consistently demonstrated that dark matter is critical not only in holding galaxies together but also in facilitating their very formation. Without its gravitational scaffolding, normal matter would remain too diffuse to collapse into the dense regions necessary for stars to ignite and galaxies to assemble. This indispensable role underscores dark matter's foundational status in the cosmic framework. An intriguing new area of research explores how variations in dark matter properties could alter galaxy formation and evolution. For instance, self-interacting dark matter, SIDM, a variant hypothesis suggesting dark matter particles occasionally collide with one another, offers solutions to specific problems arising in galaxy formation models. Such interactions might explain observed discrepancies in the density profiles of dwarf galaxies, which appear less dense at their centers than simulations based purely on non-interacting dark matter predict. Researchers continue to refine these models, using observational data to constrain the possible interactions and properties of dark matter particles. Another important observational approach involves examining dwarf galaxies orbiting larger galaxies, such as the Milky Way. These satellite galaxies, often rich in dark matter relative to their luminous matter, serve as natural laboratories for studying dark matter properties. Their dynamics, influenced heavily by unseen mass, offer clues about dark matter's distribution and behavior on smaller cosmological scales. The detailed mapping of satellite galaxies provided by missions like Gaia has already yielded invaluable insights, challenging existing models and stimulating new theories of dark matter's nature and interactions. Additionally, cosmologists and physicists consider the role of dark matter in the context of broader theories of particle physics and fundamental forces. For example, extensions to the standard model of particle physics, such as supersymmetry, predict new particles that naturally fulfill the criteria for dark matter candidates. While particle accelerators like the Large Hadron Collider, LHC, have yet to uncover direct evidence of such particles, ongoing experiments remain vital in narrowing down theoretical possibilities, continually testing and reshaping our understanding of fundamental physics and cosmology. Gravitational wave astronomy, an emerging field opened by LIGO's groundbreaking detections, also offers novel opportunities to probe the nature of dark matter. Mergers of compact objects, such as black holes or neutron stars, provide indirect constraints on the presence of dark matter through careful analyses of gravitational wave signals. The environments surrounding these cataclysmic events could potentially contain significant amounts of dark matter, influencing merger rates, wave signatures, and the precise nature of the observed signals. Thus, gravitational waves serve as a new observational window, complementing traditional electromagnetic and particle detection methods. Furthermore, future missions, such as the Euclid Space Telescope and the Vera C. Rubin Observatory, formerly LSST, promise groundbreaking observational data with unprecedented precision and depth. These observatories aim to map billions of galaxies, measure cosmic expansion, and precisely trace the distribution of dark matter throughout the universe. Such large-scale surveys will profoundly enhance our understanding, enabling scientists to rigorously test dark matter theories, constrain particle physics models, and potentially revolutionize our knowledge about this mysterious cosmic ingredient. At its core, the study of dark matter reveals a deeper philosophical insight into the scientific pursuit itself, humanity's ongoing quest to comprehend phenomena beyond immediate sensory experience. The existence of an invisible, pervasive substance that dominates cosmic structure reminds us that much of reality transcends visible boundaries, lying in realms accessible only through rigorous scientific inference, advanced technology, and creative theoretical modeling. Thus, dark matter epitomizes the inherent beauty and complexity of the universe, reflecting a fundamental truth: our observable reality, rich and detailed as it appears, is only a fragment of a much larger, more enigmatic cosmos awaiting discovery and understanding. The quest for dark matter not only reshapes our understanding of the universe but also poses fundamental questions about the limits of scientific knowledge itself. As scientists strive to unravel its nature, they confront both technological limitations and conceptual challenges, continually pushing forward the boundaries of observational astrophysics, particle physics, and theoretical cosmology. One particularly compelling avenue of contemporary research is the investigation of primordial black holes, hypothetical objects formed immediately after the Big Bang, as potential dark matter candidates. Unlike conventional stellar black holes, primordial black holes could exist across a vast range of masses and remain virtually undetectable except through their gravitational interactions. Recent gravitational lensing studies and gravitational wave detections have sparked renewed interest in this scenario, raising the intriguing possibility that dark matter might not be an exotic particle, but rather remnants from the universe's earliest moments, silently shaping cosmic evolution from the shadows. Parallel to these theoretical developments, laboratory-based experiments continue to innovate with cutting-edge detection techniques. Facilities such as Xenon, LUX Zeppelin, and the Future Darwin experiment utilize massive vats of ultrapure liquid xenon deep beneath Earth's surface, shielded from cosmic rays and background radiation, to capture elusive interactions between dark matter particles and atomic nuclei. These experiments operate on the premise that, despite dark matter's rarity of interaction, occasional collisions with ordinary matter must inevitably occur, detectable through minute energy transfers. Each year, these detectors grow in scale and sensitivity, incrementally increasing the likelihood of identifying a direct dark matter signature, an event that would revolutionize astrophysics and particle physics alike. Space-based observatories, including missions like the Fermi Gamma-Ray Space Telescope and future initiatives such as the proposed eAstrogam and AMS-02 aboard the International Space Station, contribute significantly to indirect dark matter searches. By scrutinizing the gamma-ray emissions from the centers of galaxies, dense dark matter halos, and galaxy clusters, astrophysicists hope to detect anomalies indicative of dark matter particle annihilation or decay. Although controversial claims and potential signals, such as the gamma-ray excess from the Milky Way's galactic center, have emerged, conclusive evidence remains elusive, highlighting the ongoing complexity and subtlety of dark matter interactions. Additionally, astronomical observatories employing next-generation radio telescopes, like the Square Kilometre Array, SKA, promise unparalleled sensitivity in mapping hydrogen gas distributions throughout the cosmos. By tracing hydrogen movements influenced by dark matter halos in unprecedented detail, astronomers aim to reconstruct dark matter structures in the universe's early stages, illuminating how this unseen component guided the initial formation and evolution of galaxies and large-scale structures. Furthermore, interdisciplinary collaboration has become crucial, blending astrophysics, particle physics, cosmology, and computational sciences. International teams working across continents unite expertise to run sophisticated simulations, conduct exhaustive observational campaigns, and interpret complex data sets. This collaborative model enhances scientific rigor and accelerates progress, emphasizing the global importance and profound implications of solving the dark matter puzzle. Ultimately, the search for dark matter resonates far beyond academic curiosity. Understanding dark matter's nature could provide key insights into the underlying fabric of reality itself, potentially reshaping our comprehension of fundamental physics, gravity, and cosmological evolution. It also embodies a broader narrative of human exploration and discovery, our ceaseless drive to understand the unseen, probe the unknown, and continually redefine our place within the cosmos. Dark matter, a phenomenon that we cannot directly see yet unmistakably detect through its gravitational footprints, symbolizes our collective aspiration to uncover deeper universal truths hidden beneath the visible veneer of the universe. As the investigation deepens, alternative and even radical hypotheses continue to emerge. Some researchers propose that dark matter may not be a particle at all, but rather a signal that our current understanding of gravity is incomplete. Modified Newtonian dynamics, MOND, and its relativistic extensions, like TeVis, suggest that gravity behaves differently on large scales than predicted by Einstein's general relativity. These theories attempt to explain galactic rotation curves and cosmic structure formation without invoking dark matter, instead modifying the laws of motion or gravity. While these models can replicate certain observations, they often struggle to explain the full range of cosmological data as effectively and consistently as the dark matter framework. Nonetheless, the persistence of such alternatives keeps the scientific debate alive and stimulates critical re-examinations of foundational principles. Even within the standard lambda-CDM, lambda-cold dark matter, cosmological model, refinements continue to be made. The model posits a universe composed primarily of cold, i.e., slow-moving, dark matter and dark energy, represented by the cosmological constant lambda, which drives the accelerating expansion of the universe. This model has proven remarkably successful in explaining the large-scale structure of the cosmos, the anisotropies in the cosmic microwave background, and the distribution of galaxies. However, discrepancies at smaller scales, such as the core-cusp problem and the missing satellites problem, challenge the model's completeness and motivate the exploration of alternative forms of dark matter, including warm dark matter and fuzzy dark matter, hypothetical particles with quantum properties that could smooth out small-scale structure. Beyond theoretical and observational science, dark matter inspires a profound sense of wonder in both the scientific and philosophical communities. It forces us to grapple with the idea that the overwhelming majority of matter in the universe is invisible, untouchable, and perhaps fundamentally unknowable with current tools. This has philosophical implications for how we define reality, how we interpret observation, and what it means to know something in science. It challenges the assumption that what we see is all there is, reminding us that the cosmos is deeper, darker, and more complex than human intuition often allows. Dark matter also feeds the human imagination, appearing in science fiction, art, and metaphor. In literature and film, it is often portrayed as a source of hidden power, a key to unlocking alternate realities, or a veil concealing ancient secrets. While these creative interpretations diverge from the rigor of science, they reflect a cultural resonance with the mystery and allure of the unknown. This public fascination drives curiosity, education, and support for scientific research, linking the pursuit of dark matter to broader human narratives of exploration and discovery. In educational contexts, dark matter serves as a gateway for engaging students and the public with astrophysics and cosmology. Its very invisibility makes it an ideal starting point for teaching the importance of inference, evidence, and critical thinking. Through simple analogies, such as seeing a ship's wake without seeing the ship, educators help illustrate how unseen forces can be studied through their effects. In doing so, dark matter becomes not just a research topic but a powerful teaching tool, bridging abstract concepts with tangible reasoning. As humanity's tools grow more precise and our theories more refined, the veil may one day lift, revealing dark matter in its true form. Whether it turns out to be a new type of particle, a primordial remnant, or a paradigm-shifting force beyond known physics, the discovery will mark a pivotal moment in the story of science, a moment comparable to the understanding of atoms, the discovery of galaxies, or the unveiling of the cosmic microwave background. And yet, even if dark matter remains hidden for decades to come, its gravitational influence continues to sculpt the universe around us. Every galaxy, every cluster, every filament stretching across the cosmic web is a silent testament to its presence. It surrounds us, permeates space, and binds the cosmos together, not as a shadow, but as a silent architect of cosmic destiny. This silent architect, though invisible to our eyes, has become one of the most profound revelations of modern science, a reminder that much of existence lies beyond the reach of light. The universe, once thought to be a luminous expanse of stars, galaxies, and nebulae, is now understood to be largely defined by what cannot be seen. The stars are mere tracers, drifting through the deeper gravitational seas sculpted by dark matter. In this unseen realm, galaxies take shape, dance, collide, and evolve over billions of years, following paths charted by this hidden mass. On the largest scales, dark matter is the skeleton of the cosmos. It outlines the vast cosmic web, a structure that connects galaxy clusters across unimaginable distances through filaments of dark matter and gas. Observations from weak gravitational lensing and large-scale surveys reveal the intricate geometry of this web, hinting at a deep underlying order. These colossal structures formed not from light, but from the primordial density fluctuations in the early universe, fluctuations amplified by the pull of dark matter long before stars ever ignited. Even the fate of the universe may be intertwined with the properties of dark matter. Its interplay with dark energy influences cosmic expansion, structure formation, and thermal evolution. If dark matter decays over time, or if it interacts in subtle, yet undiscovered ways, it could affect the longevity and ultimate shape of the cosmos. The balance between dark matter and dark energy may determine whether the universe continues expanding forever, slows into a gentle freeze, or tears itself apart in a dramatic finale. Meanwhile, at the scale of galaxies, dark matter protects and preserves. It forms halos that cradle spiral galaxies like the Milky Way, stabilizing their rotation and preventing their dissolution. These halos extend far beyond the visible edge of any galactic disk, invisible yet dominant. Their mass dwarfs that of the stars and gas, their gravitational field reaching out into the intergalactic void, influencing the motion of satellite galaxies, stellar streams, and even intergalactic gas clouds. The patterns observed in these motions are among the most compelling proofs of dark matter's reality. At the smallest scale, dark matter raises the possibility of entire substructures that remain hidden, dark galaxies, devoid of stars, floating in the blackness between visible galaxies. These would be made entirely of dark matter, interacting gravitationally but never shining. Simulations predict their existence, and observational efforts are ongoing to detect their gravitational influence. If confirmed, such objects would redefine the taxonomy of galactic systems and hint at a vast population of unseen companions orbiting the luminous cosmos like silent sentinels. Perhaps the most humbling realization is this: we are not made of the dominant form of matter in the universe. Everything we see, our bodies, our planet, our sun, every star and nebula, constitutes a cosmic minority. Baryonic matter, from which all known life and chemistry emerge, is a mere sliver of the total mass energy budget. The vast majority is hidden, dark matter and dark energy forming the true foundation of the universe's architecture. We are built of stardust, yes, but we drift through a universe of shadows. And yet, within those shadows, we find the deepest light, not in the form of photons, but in the form of understanding. The search for dark matter is a journey not just through space, but through the limits of knowledge, the nature of reality, and the depths of human curiosity. It is a journey that unites experiment with theory, mathematics with mystery, and observation with imagination. A journey still unfinished. The journey into the heart of dark matter is not just an exploration of the cosmos, it is an unfolding dialogue between humanity and the unknown. With each new observation, we peel back a layer of the universe's hidden structure, only to find that beneath it lies an even deeper enigma. In many ways, dark matter is both a scientific puzzle and a philosophical mirror. It reflects our limitations, our questions, and our boundless desire to understand a cosmos that consistently escapes full comprehension. In the early universe, just moments after the Big Bang, dark matter was already playing a vital role. While photons and baryons interacted through radiation pressure, creating oscillations we now observe as temperature fluctuations in the cosmic microwave background, dark matter remained unaffected, silent and inert. It began collapsing into clumps, unaffected by radiation, forming the seeds of structure before light itself could freely move. These clumps served as the gravitational anchors around which ordinary matter would eventually gather. Without this early scaffolding provided by dark matter, the universe would have remained smooth and featureless, a vast expanse of drifting particles, too uniform for complexity to emerge. In this sense, dark matter is not merely a background component. It is the hidden hand that shaped everything we now observe. The galaxies we see today are the luminous peaks of vast, invisible mountains of mass. Their formation was choreographed by the gravitational wells carved out by dark matter long before the first atoms formed. Each star that ignites, each planet that forms, and every structure that emerges owes its existence to the guiding pull of this unseen presence. It is not a peripheral mystery, it is the foundation upon which the visible universe is built. And yet, for all its cosmic power, dark matter remains eerily silent. It does not radiate. It does not absorb. It passes through us, through stars, through entire planets without a trace. This ghostly behavior makes it profoundly difficult to study. But it also sets dark matter apart as a truly unique substance, unlike anything we know, and perhaps unlike anything we can imagine. Its resistance to detection has forced scientists to develop the most sensitive instruments ever constructed, capable of sensing even the faintest whisper of an interaction. But what if dark matter is more than just a particle? Some theorists have proposed that it could be part of a hidden sector, a parallel form of matter with its own forces, its own physics, perhaps even its own version of chemistry and structure. In such models, dark matter might interact with itself more strongly than it does with our ordinary world, forming dark atoms, dark stars, even entire dark galaxies that mirror our own in eerie, invisible silence. These shadow realms would be forever separated from us except through gravity, inhabiting the same space, but never touching, never glowing. The implications of this idea are staggering. It suggests that the universe could be far richer and stranger than we ever dared believe. That the visible cosmos we study with our telescopes is just one layer of a much deeper reality, a thin film of light drifting atop a vast, unseen ocean. In this context, dark matter is not just a component of the universe, it is a second cosmos hidden beneath our feet, all around us, and yet unreachable by light. If we ever manage to detect a dark matter particle directly, it would be a moment of monumental significance, on par with the discovery of the Higgs boson or even the Copernican revolution. It would confirm the existence of a new sector of nature, opening the door to a deeper understanding of the forces and symmetries that govern all matter. It could also lead to practical breakthroughs, new physics, new energy sources, new technologies born from an understanding of matter that was once hidden from view. But even if the nature of dark matter remains elusive, its effects are undeniable. It continues to guide galaxies, shape the cosmic web, bend light across billions of light-years, and whisper through the fabric of space and time. Its gravity is the artist behind the universe's great masterpieces, the spirals of galaxies, the lattice of filaments, the dance of clusters. To study dark matter is to embrace mystery, to walk a path lit not by answers but by questions. It is to accept that we do not yet see the full picture, and yet press forward with faith in the power of observation, mathematics, and imagination. In this pursuit, science becomes not just a method, but a kind of poetry, an attempt to hear the music of a universe that sings in frequencies beyond human ears. So we listen. We search. We build detectors in the silence of deep mountains. We launch satellites into the cold void. We run simulations across supercomputers that mimic the birth of galaxies. And with every step, we draw a little closer to the truth hidden in the dark. And still, we are only beginning to comprehend the depth of the unknown. For all the progress made, the true essence of dark matter remains just out of reach, a cosmic whisper we can follow but not yet grasp. Its presence is undeniable, its influence immense, yet its identity is veiled, like a word spoken behind glass. As we advance into the next decades, a new generation of instruments and missions will push the frontier even further. The Vera C. Rubin Observatory will scan the entire visible southern sky every few nights, creating a dynamic map of the universe and tracking how structures evolve over time, structures shaped by the invisible hand of dark matter. The Euclid mission, launched by ESA, will measure the geometry of the dark universe with exquisite precision, tracing the growth of cosmic structures across space and time. NASA's Nancy Grace Roman Space Telescope will observe gravitational lensing with unparalleled resolution, revealing the dark scaffolding that holds galaxies together. Each of these missions adds another brushstroke to the portrait of the unseen, layering data, refining models, and sharpening the contours of a shadow that stretches across the cosmos. And as our measurements improve, so too do our theories. Physicists refine models of dark matter self-interaction, test new symmetries, imagine connections with the early universe, and explore the possibility that dark matter may carry the echoes of cosmic inflation or phase transitions from the earliest fractions of a second after the Big Bang. Quantum theories of gravity, string theory, and extra dimensions also enter the stage, offering speculative but mathematically rich possibilities. Could dark matter be a portal to a higher dimensional structure? Could it be a manifestation of hidden symmetries, or a residue of multiversal interactions? While these ideas may seem fantastical, they are grounded in rigorous mathematics, guided by observational constraints, and serve as blueprints for what might lie beyond the current horizon of understanding. In parallel, the human story unfolds. The study of dark matter is not the work of isolated geniuses in ivory towers, but of global collaborations, physicists, engineers, computer scientists, and students working together across cultures and continents. Data flows across oceans. Discoveries are shared in real time. Young minds are inspired by the mystery of the invisible. In classrooms and lecture halls, the question, "What is dark matter?" ignites curiosity that echoes across generations. And still, behind this collective effort lies something deeply personal. The search for dark matter is, at its core, a reflection of our nature as seekers. We are drawn to the stars not only to map their light, but to understand what binds them together. We are not content with what is visible. We long to know what lies beyond. Dark matter, in all its silence, speaks directly to that longing. It reminds us that the universe is larger, stranger, and more beautiful than we imagined, that truth is not limited to what we can see, but includes what we can infer, what we can imagine, and what we can one day discover. The cosmos is not complete without its shadows. And perhaps we are not complete without the pursuit of them. For in chasing the darkness, we illuminate what it means to be human, to wonder, to question, to reach. As we peer farther into space, we also peer further back in time. Light from distant galaxies takes billions of years to reach us, and in that light we see echoes of the young universe, its turbulence, its birth cries, its first great structures arising. What we find again and again is that dark matter was already there. Long before stars were born, before the first galaxies took shape, dark matter had already begun weaving the invisible framework of reality. The James Webb Space Telescope, with its unparalleled ability to observe the earliest epochs of galaxy formation, is beginning to reveal galaxies from a time when the universe was only a few 100 million years old. Yet even these ancient structures appear too massive, too evolved, to have formed from ordinary matter alone. Their presence confirms what cosmologists have long suspected: dark matter accelerated the assembly of structure, allowing galaxies to emerge earlier and grow faster than visible matter would allow on its own. In this way, dark matter acts like a silent catalyst, enabling complexity, forging order from chaos, guiding the transformation of a smooth early universe into a vast, dynamic cosmos. And yet, it does so without light. That is perhaps its most haunting quality: it does not glow, and it does not shine. It is not radiant like the stars. It is not explosive like supernovae. It makes no sound and leaves no trail of color. But in its silence, it sculpts. In its stillness, it governs the motions of galaxies, dictates the shape of the web that binds them, and underwrites the expansion and evolution of the entire cosmos. Some have begun to wonder, could dark matter even influence life? If galaxies could not have formed without dark matter, then neither could stars, planets, or the environments in which life arises. In this indirect but profound way, dark matter may be a prerequisite for existence itself. Life, consciousness, even the act of observing the universe, all of it may be possible only because an invisible substance we cannot touch or see laid the foundation for cosmic architecture billions of years before we were born. This possibility elevates dark matter from a scientific curiosity to something more profound, a cosmic condition of our very being. The atoms that compose our bodies follow the gravitational paths determined by dark matter. Our Sun orbits the center of the Milky Way not in empty space, but within a dark halo of unseen mass. Every motion we make, every step, every breath, is part of a chain of consequences made possible by this mysterious matter. We are creatures of light, but we are held together by the dark. And still, we are just beginning to ask the right questions. What if dark matter interacts with dark energy in ways we haven't imagined? What if it has a complex internal structure, its own physics, its own laws, perhaps even its own forms of organization beyond anything we know? Some theories suggest it might clump, oscillate, form vortices, or exhibit quantum behaviors on galactic scales. Others explore whether the boundary between dark matter and ordinary matter is as clear as we think, or whether some forms of matter may exist in a liminal state, sharing properties of both. In the shadows, there may be layers of structure we cannot yet detect, echoes of higher dimensional geometries or hidden symmetries that tie together matter, energy, and spacetime in ways our current theories can only glimpse. These ideas stretch the imagination and the edges of our mathematics, but they reflect a larger truth: the universe is not finished revealing itself. And neither are we finished seeking. With every new telescope, every deep space probe, every underground detector, and every equation on a physicist's blackboard, we inch closer to the heart of the unknown. Perhaps we will one day isolate a dark matter particle in a laboratory, hold its signature in our instruments, and finally speak its name. Or perhaps it will forever remain beyond our grasp, a permanent veil that reminds us of the cosmos's infinite depth. As our knowledge expands, so too does our humility. For all our technology, for all our theories, there remains something almost sacred in the way dark matter refuses to reveal itself directly. It is as if the universe has written its story in layers, some bright and loud, others whispered in forces and distortions, felt but never seen. And dark matter is that whisper, echoing through every corner of the cosmos, a quiet rhythm beneath the brilliance of stars. When we look at the motions of galaxies, we are not just charting their paths, we are tracing the fingerprint of the unseen. When we observe clusters bending the light of galaxies behind them, we are witnessing space itself curve under the weight of something that does not shine. It is through these distortions and deviations that we come to know what we cannot see. In this sense, dark matter becomes a kind of cosmic poetry, written not in words, but in gravitational pull, in structure, in form. And yet, for all its power, dark matter is astonishingly indifferent. It does not burn, it does not bind into atoms, it does not form molecules. It flows through walls, through stars, through you and me, leaving no trace, save for its pull. It is a force without touch, a presence without light, and in that, it may be the purest form of being. Not as something that is, but as something that acts, a principle of motion, a sculptor of form, a silent hand behind the cosmic loom. This brings us to the deep philosophical questions dark matter awakens. What does it mean to be real? Is existence defined by what we can see, or by what we can measure, predict, and feel through its influence? Dark matter forces us to confront the limitations of perception, to accept that reality does not conform to human senses. It reminds us that we are creatures living in the light, but that most of reality exists in shadow, not in darkness as absence, but in darkness as mystery. In a strange way, the invisible world of dark matter reflects something within us as well. We too are shaped by unseen forces, memory, thought, gravity, time. We build cities, empires, civilizations, yet behind every act of creation there are deeper patterns, the mind's gravity, the soul's orbit, the unspoken structures of emotion and intuition. Dark matter in the universe, like the hidden frameworks within us, gives rise to all that is visible, meaningful, and alive. Perhaps this is why we are so drawn to it. Not just as scientists, but as humans. We look into the night sky and know instinctively that what we see is not all there is. That behind the starlight, behind the constellations and nebulae, lies something more, something deeper, older, essential. The dark is not to be feared. It is to be explored. It is the canvas upon which the stars are painted, the silence upon which the music of the galaxies plays. And still, the search continues. Beneath mountains, in the heart of detectors chilled to near absolute zero, deep in the dark of Earth and far in the black of space, we listen. We wait. We refine. Each failed detection is not defeat, it is progress, narrowing the possible, focusing the question. And each new signal, each anomaly, each unexpected twist in data, is a doorway. A whisper. An invitation. Dark matter may yet hold the key to unifying gravity with quantum mechanics, to explaining the fate of the universe, or even to discovering realms of physics we have not imagined. But beyond that, it holds a mirror to our essence, that we are beings who search, who question, who walk into the unknown not for answers alone, but because the act of seeking itself defines us. Each step into the unknown deepens our sense of awe. As we uncover more about the structure of the universe, we realize that dark matter is not an exception, it is the rule. The light of stars is the embroidery. The shadow, the weave. It holds the framework together. It is the gravitational skeleton upon which galaxies hang like lanterns. Without it, the universe would collapse into disorder, or never form at all. In a way, dark matter is the cosmos' most faithful guardian. Unchanging, silent, and constant, it shepherds stars along their orbits, it binds clusters into families, it supports the filamentous structure of the cosmic web. It asks for nothing. It simply is. Not as something to be seen, but as something to be trusted. For every time we measure the motions of a galaxy, every time we detect the bending of light, we reaffirm its presence. It has never failed us. It simply defies our reach. And perhaps it is not meant to be found easily. Perhaps dark matter teaches us the value of patience, of science not as instant revelation but as slow, persistent listening. The universe does not shout its secrets. It murmurs them across billions of years, in gravity, in structure, in silence. And we, small beings on a pale blue dot, have learned to hear that silence. In this silence there is beauty. Not the radiant beauty of a nebula or the explosive drama of a supernova, but the quiet, enduring beauty of presence without recognition. Dark matter, like deep time, like the void between galaxies, asks us to reconsider what matters. It invites us to wonder not only what the universe is made of, but why it is shaped this way at all. Are we here because of the conditions dark matter made possible? Was it the hidden hand that tilted the odds in favor of complexity, of chemistry, of life? Without its gravity, would the stars have gathered? Would planets have formed? Would biology have had a canvas on which to draw its blueprints? These are not just physical questions, they are existential ones. To understand dark matter is to ask how the visible and the invisible collaborate to produce a universe not only capable of stars, but of meaning. In the end, dark matter reminds us that there is more to existence than brightness and brilliance. That the most essential truths may lie in what cannot be seen, only inferred. That the invisible can be real, and the unknowable can be felt. And that perhaps, at the heart of the cosmos, there is not just energy or matter, but mystery itself. And so we search. We build instruments that listen for whispers in the night. We design algorithms that trace patterns in the chaos. We send questions into the dark, and we wait for the universe to answer in the language it speaks best: motion, gravity, structure, silence. For now, dark matter remains nameless. But it is not absent. It is the breath between the stars. The pause between each heartbeat of the cosmos. And it is calling, not to be solved, but to be pursued. Dark matter is more than a scientific mystery. It is a threshold. A liminal space between what we know and what we sense, between the illuminated world and the deeper forces that hold it in place. It does not reveal itself easily, yet it governs the grandest structures in existence. It does not shine, yet without it, there would be no stars to shine at all. It is the unseen weight of the cosmos, the silent architecture behind every galaxy, every cluster, every gravitational echo we can trace across time and space. Its influence is written into the rotation of spiral arms, the warping of spacetime, the dance of satellite galaxies, the very scaffolding of the observable universe. It holds everything, and yet, it withholds itself. In its elusive nature, dark matter teaches us something profoundly human, that truth is not always visible, and meaning is not always found in what is bright. That there is value in searching, even when the object of our search evades us. That some of the most powerful forces in existence are silent, invisible, and endlessly patient. And so, our journey continues. Each generation of scientists adds a new lens, a new theory, a new question to the long unfolding story. Each failure to detect becomes a refinement. Each anomaly becomes a clue. In caverns beneath the earth, in satellites above the atmosphere, in supercomputers that simulate the universe from its first moment to its distant future, the search persists. Not because we are lost, but because we are drawn forward by the very gravity of not knowing. For what is dark matter if not a symbol of the vastness that remains? A reminder that we are still discovering what the universe is made of, and perhaps, what we are made for. We are beings shaped by curiosity, pulled by mystery, made restless by the horizon. And so we reach, always further, always deeper, into the space between light and shadow. Maybe one day we will name it. Maybe we will hold a particle in our hands, or map its structure with perfect precision. But even if we never do, dark matter will remain, the invisible foundation, the quiet force, the hidden story behind all that is. A story not of darkness, but of depth. Of structure. Of wonder. And of the beautiful, endless act of reaching into the unknown. Pulsars are among the most fascinating and enigmatic objects in the universe, captivating scientists and enthusiasts alike with their sheer precision, immense power, and unique role in our understanding of the cosmos. These spinning neutron stars, the remnants of massive stars that have undergone supernova explosions, are cosmic lighthouses that emit beams of electromagnetic radiation, radio waves, X-rays, or even gamma rays, sweeping through space with astonishing regularity. To fully grasp the significance of pulsars and their mighty beams, we must delve into their origins, characteristics, mechanisms, and the profound impact they have on modern astrophysics. At their core, pulsars are neutron stars, which are themselves the remnants of stars that once burned with incredible intensity. When a star with a mass significantly greater than that of our Sun reaches the end of its life, it undergoes a cataclysmic explosion known as a supernova. During this event, the outer layers of the star are expelled into space, while the core collapses under the force of gravity. This collapse compresses the core to an extraordinary density, creating a neutron star. To put this density into perspective, a single sugar cube-sized piece of neutron star material would weigh about 1 billion tons on Earth. Neutron stars are extraordinary in many ways. They are incredibly small, typically only about 20 kilometers, 12 miles, in diameter, yet they can contain more mass than our Sun. This extreme compactness leads to gravitational forces so strong that the surface gravity of a neutron star is billions of times greater than Earth's. The intense gravitational compression also causes the rotation of the neutron star to speed up dramatically. Much like a figure skater pulling in their arms to spin faster, the collapsing core of a dying star conserves angular momentum, leading to the rapid rotation that is a hallmark of pulsars. The rapid rotation is only part of the story. What makes pulsars truly remarkable are their powerful magnetic fields. These magnetic fields are trillions of times stronger than Earth's and play a crucial role in the pulsar's behavior. As the neutron star rotates, its magnetic field generates beams of electromagnetic radiation along its magnetic poles. These beams are not aligned with the star's rotational axis, meaning they sweep across space like the beams of a lighthouse. When one of these beams crosses Earth's line of sight, we detect a pulse of radiation, giving pulsars their name. The discovery of pulsars dates back to 1967 when Jocelyn Bell Burnell, a graduate student at the University of Cambridge, first observed a series of regular radio pulses while analyzing data from a radio telescope. These pulses were so precise that they were initially dubbed LGM, short for Little Green Men, as some speculated they could be signals from an intelligent extraterrestrial civilization. However, further observations revealed that these signals were natural phenomena, marking the birth of pulsar astronomy. Pulsars are often described as nature's most precise clocks. Some spin hundreds of times per second, emitting pulses with such regularity that they rival the accuracy of atomic clocks. This precision makes pulsars invaluable tools for a variety of scientific endeavors. For instance, they can be used to test the predictions of Einstein's theory of general relativity, study the interstellar medium, and even detect gravitational waves. The regularity of pulsar signals has also led to proposals for using them as navigation beacons for interstellar spacecraft, providing a cosmic GPS system for future explorers. One of the most extreme types of pulsars is the millisecond pulsar, which rotates hundreds of times per second. These pulsars are believed to have been spun up by accreting material from a companion star in a binary system. The transfer of mass and angular momentum from the companion star increases the pulsar's rotation rate, creating a cosmic dynamo that emits pulses at mind-boggling frequencies. Millisecond pulsars are particularly useful for studying gravitational waves, as their incredible timing precision allows scientists to detect minute disturbances in spacetime caused by the merging of supermassive black holes. Another fascinating aspect of pulsars is their role in the universe's life cycle. As pulsars emit radiation and particles, they lose energy, causing their rotation to gradually slow down over time. This process, known as spin-down, eventually leads to the pulsar becoming a dead neutron star, no longer emitting detectable pulses. However, the energy emitted during a pulsar's active phase can have profound effects on its surroundings. Pulsars can power spectacular phenomena such as pulsar wind nebulae, where charged particles accelerated by the pulsar's magnetic field create glowing clouds of gas and dust. One famous example is the Crab Nebula, which is powered by the Crab pulsar, a young and energetic neutron star at its center. Pulsars also provide a unique window into the fundamental laws of physics. The extreme conditions on and around pulsars, such as their immense gravity, density, and magnetic fields, cannot be replicated in any laboratory on Earth. This makes them natural laboratories for studying the behavior of matter and energy under the most extreme circumstances. For example, the interiors of neutron stars are thought to contain exotic states of matter, such as quark-gluon plasma or superfluid neutrons, that challenge our current understanding of particle physics. In recent years, the study of pulsars has entered a new era with the advent of advanced telescopes and detection methods. Radio telescopes such as the Square Kilometre Array, SKA, and space-based observatories like the Fermi Gamma Ray Space Telescope have expanded our ability to observe pulsars across the electromagnetic spectrum. These instruments have not only discovered hundreds of new pulsars but also revealed unexpected phenomena, such as pulsars that emit X-rays or gamma rays in addition to radio waves. These multi-wavelength observations are helping scientists piece together a more complete picture of how pulsars work and their role in the cosmos. One of the most exciting developments in pulsar astronomy is the use of pulsars to detect gravitational waves. When massive objects such as black holes or neutron stars collide, they generate ripples in spacetime that propagate across the universe. By carefully monitoring the timing of pulses from an array of millisecond pulsars, known as a pulsar timing array, scientists can detect the subtle changes caused by passing gravitational waves. This technique complements the work of ground-based detectors like LIGO and Virgo, offering a new way to explore the universe's most violent events. Pulsars are not just scientific curiosities, they also hold profound philosophical implications. They remind us of the incredible diversity and complexity of the universe, as well as the interconnectedness of its phenomena. The same physical laws that govern the behavior of atoms and molecules on Earth also dictate the formation and evolution of stars, the dynamics of galaxies, and the mysterious workings of neutron stars. By studying pulsars, we gain a deeper appreciation for the beauty and unity of the cosmos. In conclusion, pulsars and their mighty beams are a testament to the power and precision of nature. These spinning neutron stars, born from the ashes of supernovae, serve as cosmic lighthouses, laboratories, and clocks, illuminating the mysteries of the universe. As our understanding of pulsars continues to grow, so too does our ability to unlock the secrets of the cosmos, from the tiniest particles to the grandest structures. The story of pulsars is far from over, and their study promises to reveal even more about the nature of reality in the years to come. The exploration of pulsars continues to yield groundbreaking discoveries that deepen our understanding of the universe, pushing the boundaries of astrophysics and opening new avenues of research. At the heart of this progress is the relentless quest to understand the physics behind these remarkable objects and their applications in unraveling the mysteries of the cosmos. One of the key areas of ongoing research focuses on the structure and composition of neutron stars themselves. Despite their seemingly straightforward classification as superdense remnants of massive stars, the internal structure of neutron stars remains a profound mystery. At their cores, the densities are so extreme that matter exists in forms entirely unlike anything we encounter on Earth. Scientists theorize that the core of a neutron star may consist of exotic states of matter, such as a quark soup, where protons and neutrons dissolve into their constituent quarks. Alternatively, the cores could contain hyperons, particles that include strange quarks, or even more speculative forms of matter like boson condensates or strange matter, a state hypothesized to be more stable than regular atomic nuclei. To probe these possibilities, researchers rely on both observational data and theoretical modeling. Observations of pulsars in binary systems, where they orbit another star, provide critical information. By measuring the pulsar's mass and radius with extreme precision, scientists can constrain the equation of state, EOS, of nuclear matter, which describes how matter behaves at such high densities. Recent breakthroughs in this area have been achieved using the Neutron Star Interior Composition Explorer, NICER, an instrument aboard the International Space Station. NICER has provided detailed measurements of X-ray emissions from pulsars, allowing researchers to map their surface temperatures and infer their sizes. Another powerful tool in the study of pulsars is gravitational wave astronomy. When two neutron stars in a binary system spiral toward each other and eventually merge, they emit gravitational waves that ripple across the fabric of spacetime. The detection of these waves by observatories like LIGO and Virgo has already provided groundbreaking insights. For example, The famous event GW 170817, observed in 2017, was the first detection of a neutron-star merger and was accompanied by electromagnetic signals, including gamma rays, X-rays, and visible light. This multi-messenger observation confirmed that such mergers are a primary source of heavy elements like gold and platinum in the universe. Studying the gravitational waves from neutron-star mergers also helps scientists understand the physics of matter under extreme conditions, offering indirect insights into the interiors of neutron stars. Pulsars also serve as exceptional tools for studying the interstellar medium, ISM, the vast expanse of gas, dust, and plasma that fills the space between stars. As the radio pulses from a pulsar travel through the ISM, they interact with the charged particles in the medium, causing a phenomenon known as dispersion. High-frequency waves travel faster than low-frequency waves, leading to a delay in the arrival times of different frequencies. This dispersion provides a cosmic fingerprint of the ISM's density and composition along the line of sight to the pulsar. By analyzing these dispersion effects, astronomers can create detailed maps of the ISM, revealing its structure and dynamics on both small and large scales. Beyond their utility as scientific tools, pulsars are also valuable in testing the fundamental laws of physics. One of the most intriguing applications is their use in probing the limits of Einstein's general theory of relativity. While general relativity has passed every test to date, it is still an incomplete theory, as it does not incorporate quantum mechanics. Pulsars in binary systems, especially those paired with another neutron star or a white dwarf, create natural laboratories for testing the effects of strong gravitational fields. The orbits of these binary systems can be measured with extraordinary precision, allowing scientists to detect tiny deviations from predictions based on general relativity. For instance, the timing of pulses from the Hulse-Taylor binary pulsar provided the first indirect evidence for the existence of gravitational waves, earning its discoverers the 1993 Nobel Prize in Physics. Millisecond pulsars, the fastest spinning pulsars, have opened yet another frontier in astrophysics. Their incredible stability and rapid rotation make them ideal for use in pulsar timing arrays, PDAs, networks of pulsars monitored to detect gravitational waves from supermassive black hole mergers. Unlike the high-frequency waves detected by LIGO and Virgo, these waves are in the nanohertz range, corresponding to events that unfold over millions of years. PDAs are effectively a galactic-scale gravitational wave detector, with the potential to uncover the population and behavior of supermassive black holes in distant galaxies. Recent advances in radio astronomy have significantly enhanced our ability to study pulsars. The Square Kilometre Array, SKA, currently under construction, promises to revolutionize pulsar research. With its unprecedented sensitivity and ability to survey large portions of the sky quickly, the SKA is expected to discover tens of thousands of new pulsars, including rare and exotic types. This will greatly expand our understanding of the pulsar population, their birth and evolution, and their role in the broader context of galactic and extragalactic phenomena. In addition to radio telescopes, space-based observatories are playing an increasingly important role in pulsar research. The Fermi Gamma Ray Space Telescope has detected dozens of pulsars that emit gamma rays, revealing a population of gamma-ray-only pulsars that were invisible to traditional radio telescopes. These discoveries have shed light on the high-energy processes that occur in the magnetospheres of pulsars, where particles are accelerated to near-light speeds and emit intense radiation. Future missions, such as the proposed Einstein probe, aim to explore the X-ray and gamma-ray universe with even greater sensitivity, potentially uncovering new classes of pulsars and neutron stars. The study of pulsars is also driving advancements in technology and computation. The vast amounts of data generated by modern telescopes require sophisticated algorithms and machine learning techniques to process and analyze. For example, the search for pulsars in the dense cores of globular clusters or near the galactic center involves sifting through millions of potential signals to identify genuine pulsars. These efforts are not only advancing astrophysics but also contributing to fields like artificial intelligence and big data analysis. In the realm of speculative research, scientists are exploring the possibility of using pulsars for interstellar navigation. The regularity of pulsar signals makes them ideal as natural beacons, allowing spacecraft to determine their position with high accuracy. This concept, known as pulsar-based navigation, has already been demonstrated in principle by NASA's NICER experiment, which successfully used X-ray signals from pulsars to determine the location of the International Space Station. Finally, pulsars hold the potential to answer some of the most profound questions in science, such as the nature of dark matter and the origin of the universe's magnetic fields. Some theories suggest that interactions between pulsars and hypothetical particles, like axions or dark photons, could provide indirect evidence for dark matter. Similarly, studying the magnetic fields of pulsars may offer clues about how magnetic fields are generated and sustained on cosmic scales. In every sense, pulsars are more than just remnants of dead stars. They are dynamic, powerful, and endlessly intriguing objects that connect us to the fundamental workings of the universe. As research continues to push the boundaries of what we know, pulsars stand as a testament to humanity's enduring curiosity and our ability to unlock the secrets of the cosmos. The fascination with pulsars stems not only from their exotic nature but also from their profound implications for our understanding of physics, astrophysics, and the evolution of the universe. These celestial phenomena, though born in the fiery deaths of massive stars, are far from inert remnants. They are dynamic laboratories where the laws of nature are pushed to their absolute limits. As our technology advances, we are entering an era of pulsar exploration that promises to unravel mysteries we once thought impenetrable. One of the most intriguing questions surrounding pulsars concerns their magnetic fields, which are among the strongest in the universe. These fields can reach intensities of up to 10^1 Gauss, billions of times stronger than the Earth's magnetic field. These extreme magnetic environments lead to the creation of magnetars, a rare and highly energetic class of neutron stars. Magnetars are capable of releasing massive amounts of energy in the form of gamma-ray bursts and X-rays, often in catastrophic events known as starquakes. These quakes occur when the immense magnetic field distorts the star's crust, causing it to crack and release bursts of energy detectable from across the galaxy. Understanding magnetars not only sheds light on the physics of ultra-strong magnetic fields but also helps explain some of the most energetic events in the universe. One particularly puzzling aspect of pulsars is the phenomenon of pulsar glitches. Despite their incredible precision as cosmic clocks, many pulsars exhibit sudden, unexpected increases in their rotational speed. These glitches are thought to occur due to interactions between the pulsar's solid crust and its superfluid interior. The superfluid, a state of matter with zero viscosity, can decouple from the crust, causing a rapid transfer of angular momentum. Studying these glitches provides a rare opportunity to probe the interior dynamics of neutron stars, offering insights into the behavior of matter under conditions that cannot be replicated in any terrestrial laboratory. The connection between pulsars and gravitational waves is another area of active research that continues to captivate scientists. While the detection of individual binary neutron star mergers has already transformed our understanding of these cosmic behemoths, the long-term monitoring of pulsars through pulsar timing arrays, PDAs, holds the promise of detecting a background hum of gravitational waves permeating the universe. This background is thought to arise from the mergers of supermassive black holes in the centers of distant galaxies. Each pulsar in a PDA acts as a cosmic metronome, and deviations in their timing can reveal the passage of gravitational waves. Detecting this background would not only confirm the prevalence of supermassive black hole binaries but also provide insights into galaxy formation and evolution. The role of pulsars in the hunt for dark matter is another frontier that sparks the imagination. Dark matter, an elusive form of matter that makes up about 27% of the universe, has so far eluded direct detection. Pulsars, with their extreme environments, may offer a way to study dark matter indirectly. For instance, some theories predict that dark matter particles could accumulate in the dense cores of neutron stars, altering their properties in detectable ways. Alternatively, pulsars could emit gamma rays through interactions with dark matter particles, such as annihilation or decay. Observatories like the Fermi Gamma Ray Space Telescope are actively searching for such signals, which could provide the first concrete evidence of dark matter. Pulsars also serve as key tools in the study of cosmic rays, high-energy particles that constantly bombard the Earth from space. These particles originate from some of the most energetic processes in the universe, including supernovae and the winds of pulsars. By studying the spectra of pulsar wind nebulae, glowing regions of gas and particles accelerated by pulsar winds, scientists can gain insights into the mechanisms that drive particle acceleration to extreme energies. This research not only deepens our understanding of pulsars but also sheds light on the broader processes that shape the high-energy universe. The discovery of fast radio bursts, FRBs, enigmatic millisecond-long flashes of radio waves, has added another layer of intrigue to pulsar research. While FRBs are not directly tied to pulsars, their brief, intense bursts share similarities with pulsar emissions. Some theories propose that magnetars or highly active young pulsars could be responsible for at least a subset of FRBs. The study of these bursts, which originate from billions of light-years away, has become one of the hottest topics in astrophysics, offering a tantalizing glimpse into the workings of the distant universe. In addition to advancing our understanding of the cosmos, pulsars are inspiring technological innovations. The use of pulsar signals for navigation, for example, has already been demonstrated in space missions. By triangulating signals from multiple pulsars, spacecraft could determine their position with remarkable accuracy, even far beyond our solar system. This pulsar-based navigation is a cornerstone of proposed interstellar travel concepts, providing a robust and autonomous system for guiding spacecraft across vast cosmic distances. The future of pulsar research is set to be transformed by next-generation observatories. The Square Kilometre Array, SKA, once operational, will be the most sensitive radio telescope ever built, capable of detecting faint pulsars in distant galaxies and uncovering entirely new populations of these objects. Meanwhile, advanced X-ray observatories like Athena and gamma-ray instruments like the Cherenkov Telescope Array, CTA, will provide unprecedented views of the high-energy universe, allowing scientists to study pulsars and their environments in exquisite detail. Even as we expand our observational capabilities, theoretical research is pushing the boundaries of what we know about pulsars. Simulations of neutron star mergers, for example, are becoming increasingly sophisticated, revealing the complex interplay of gravity, nuclear physics, and magnetohydrodynamics. These models are helping scientists interpret observational data and predict new phenomena, such as the production of short-lived hypermassive neutron stars that may briefly form after a merger before collapsing into a black hole. Pulsars also serve as a poignant reminder of the interconnectedness of the universe. The elements that make up our planet and our bodies, such as carbon, nitrogen, and oxygen, were forged in the cores of stars and distributed across the cosmos in supernova explosions. Pulsars, as the remnants of these stellar cataclysms, are not only cosmic relics but also active participants in the ongoing cycle of star formation and evolution. Their powerful winds and radiation shape their surrounding environments, influencing the formation of new stars and planets. Ultimately, pulsars are far more than astronomical curiosities. They are cosmic beacons that illuminate the fundamental forces of nature, from gravity and magnetism to the behavior of matter at its most extreme. They challenge our understanding of the universe and inspire us to push the limits of technology and imagination. As we continue to explore these enigmatic objects, we are not only uncovering the secrets of the cosmos but also deepening our connection to the universe and our place within it. The study of pulsars is a testament to humanity's unyielding curiosity and our ability to transcend the boundaries of what we know, reaching ever closer to the ultimate truths of existence. Pulsars captivate us because they are not just remnants of the stars that came before us, they are engines of cosmic wonder, spinning faster than the eye can comprehend and emitting beams of energy that have traveled across eons to reach us. Their existence beckons us to understand the extreme, where physics bends, reality warps, and the universe reveals its most profound secrets. Imagine a world where time itself becomes elastic, warped by gravity so intense that a teaspoon of material weighs more than an entire mountain. This is the realm of pulsars, where the interplay of mass, energy, and magnetism creates phenomena that defy intuition. Pulsars are nature's most efficient power generators, converting the rotational energy of a collapsing star into focused beams of radiation that can span the electromagnetic spectrum. It's no wonder they are described as cosmic lighthouses, yet even this poetic description barely scratches the surface of their astonishing nature. But pulsars are not just powerful, they are precise. The fastest known millisecond pulsars rotate at speeds of over 700 times per second, with their beams pulsing with such consistency that they rival atomic clocks in precision. Scientists have tapped into this stability to explore the universe in ways previously unthinkable. By measuring minuscule shifts in the timing of these pulses, astronomers have begun detecting gravitational waves rippling across spacetime, caused by the mergers of supermassive black holes billions of light-years away. Every pulse from a distant pulsar carries with it a signature of the universe's history, a ticking metronome that spans cosmic time. The intrigue deepens as we realize that pulsars are messengers from the edge of the known. They thrive in environments so extreme that conventional physics teeters on collapse. The temperatures on a pulsar's surface can reach millions of degrees, while its magnetic field could strip atoms apart. Even light bends under the crushing weight of its gravity, giving rise to effects like gravitational lensing, where the pulsar's own photons curve around it, making it visible even from behind. One of the most compelling mysteries in pulsar research is the nature of their magnetic fields. The strongest pulsars, known as magnetars, emit bursts of energy so powerful they can disrupt satellites and ionize Earth's upper atmosphere, even from thousands of light-years away. These starquakes release more energy in a fraction of a second than our Sun emits in 100,000 years. Yet, magnetars are still poorly understood. Why do some neutron stars become magnetars while others do not? What mechanisms power their devastating bursts? Answering these questions could unlock the secrets of magnetic fields across the universe, from planets to galaxies. And then there are the glitches, those sudden, puzzling changes in a pulsar's rotation rate. These glitches are thought to be the result of the superfluid interior of the neutron star interacting with its rigid crust, releasing pent-up energy. Each glitch is like a seismic tremor on Earth, but on a scale so vast it could affect the spin of an entire star. These events give us rare glimpses into the hidden interiors of pulsars, where the laws of quantum mechanics collide with the macroscopic forces of gravity. Pulsars are also key to understanding how stars die and galaxies evolve. As they spin down and age, pulsars lose energy, eventually fading into obscurity. But in their active lifetimes, they shape their environments profoundly. Pulsar wind nebulae, created by the outflow of energetic particles from the star, are some of the most beautiful and dynamic structures in the universe. The Crab Nebula, illuminated by the Crab pulsar at its center, is a prime example, a glowing cloud of charged particles stretching across space, powered by the pulsar's unrelenting rotation. But pulsars don't live in isolation. Some exist in binary systems, orbiting a companion star. These partnerships are fertile ground for astrophysical discovery. When a pulsar accretes matter from its companion, it can spin up, becoming a millisecond pulsar, a rejuvenated stellar corpse that now spins faster than ever. Binary pulsars also allow for the precise testing of Einstein's general theory of relativity. In these systems, the orbits are so compact and the gravitational fields so strong that relativistic effects become measurable. Tiny deviations in the pulsar's timing confirm the predictions of general relativity, such as time dilation and the emission of gravitational waves. Even beyond their scientific value, pulsars are reshaping our vision of the future. NASA has already demonstrated that pulsar signals can be used for spacecraft navigation, effectively turning these cosmic lighthouses into a galactic GPS system. Imagine a future where interstellar spacecraft chart their courses by tuning into the radio pulses of distant pulsars, navigating the stars with precision and autonomy. The universe itself becomes a map, etched in the rhythmic pulses of dead stars. As technology advances, so too does our ability to study pulsars in unprecedented detail. The square-kilometer array will allow astronomers to detect faint pulsars hiding in the most distant corners of the universe. High-energy observatories like the Cherenkov Telescope Array will probe the gamma-ray emissions of pulsars, uncovering the mechanisms behind their immense power. Machine learning algorithms are already being employed to sift through vast datasets, identifying new pulsars and revealing previously unseen phenomena. And yet, despite all we have learned, pulsars remain shrouded in mystery. Could they harbor clues to the nature of dark matter? Some theories suggest that pulsars might interact with dark matter particles, creating observable signals. Could pulsars be used to study the elusive axion, a hypothetical particle that could solve long-standing problems in quantum physics? Every new discovery seems to deepen the mystery, opening doors to questions we never thought to ask. Pulsars are not just scientific objects, they are gateways to wonder. They remind us that the universe is far stranger and more beautiful than we can imagine. They are proof that even in death, stars can shine brighter than ever, casting their light across the cosmos and enriching our understanding of existence. For every question we answer, pulsars pose 10 more, daring us to look deeper and dream bigger. The journey of studying pulsars is far from over, it is just beginning. These spinning remnants of ancient stars are more than celestial curiosities, they are the keepers of cosmic secrets, waiting to be unlocked by those bold enough to search. And as we peer deeper into the night sky, following the rhythmic pulse of these distant lighthouses, we are reminded that the universe is alive with discovery, and we are only just learning to listen. The allure of pulsars lies not only in their scientific significance but also in their ability to connect us to the universe's most profound and extreme phenomena. Each pulsar, in its rhythmic and unyielding pulse, tells a story of cosmic violence, survival, and the intricate dance of fundamental forces shaping the fabric of reality. As we continue to study these enigmatic objects, we uncover layers of complexity that challenge even the most established theories, opening new pathways to understanding the cosmos. One of the most tantalizing questions in pulsar research revolves around their formation. When a massive star ends its life in a supernova explosion, the core collapses into a neutron star. However, not all neutron stars become pulsars. Some remain as quiet, cooling objects, while others ignite into the brilliant, spinning lighthouses we know as pulsars. What determines whether a neutron star will become a pulsar? Is it the star's mass, its spin rate, or the configuration of its magnetic field? These questions remain unanswered, but they hold the key to understanding not just pulsars but the life cycles of stars and the broader processes that shape galaxies. The role of pulsars in the ecology of the galaxy cannot be overstated. As pulsars emit powerful winds of charged particles, they inject energy into their surroundings, influencing the formation of new stars and even planetary systems. In some cases, these winds carve out massive bubbles in the interstellar medium, creating stunning structures visible across vast distances. These pulsar wind nebulae are not just beautiful, they are laboratories for studying high-energy physics, particle acceleration, and the behavior of magnetic fields on cosmic scales. Pulsars also play a crucial role in the search for exoplanets. While pulsars are hostile environments for life as we know it, their extreme stability makes them excellent tools for detecting the faint gravitational effects of orbiting planets. In fact, the first exoplanets ever discovered were found around a pulsar, PSR B1257+12, in 1992. These planets, likely the remnants of a destroyed companion star, orbit their pulsar with incredible precision, providing a unique glimpse into the resilience of planetary systems in extreme conditions. The discovery of pulsar planets has opened the door to speculation about the nature of life in the universe. Could exotic forms of life exist on planets orbiting pulsars, shielded from the deadly radiation by thick atmospheres or magnetic fields? While this remains purely speculative, it underscores the endless possibilities that pulsars present for exploring the boundaries of what is possible in the universe. Beyond their astrophysical significance, pulsars challenge our understanding of the fundamental nature of reality. In the extreme environments of pulsars, where densities rival those of atomic nuclei and magnetic fields reach unimaginable intensities, the familiar laws of physics begin to break down. These are places where quantum mechanics and general relativity collide, offering a glimpse into the elusive theory of quantum gravity that scientists have sought for decades. By studying pulsars, we are not just learning about stars, we are probing the very foundations of the universe. One of the most exciting frontiers in pulsar research is the use of artificial intelligence and machine learning to uncover new pulsars. With modern radio telescopes generating terabytes of data every day, finding pulsars has become a task that requires advanced computational tools. Algorithms trained to recognize the unique signatures of pulsars in noisy data have already discovered dozens of new objects, including rare and exotic types that were previously missed. These discoveries are expanding our understanding of the pulsar population and revealing new insights into their origins and evolution. In recent years, pulsar research has also ventured into the realm of multi-messenger astronomy, where observations across multiple wavelengths and messengers, such as electromagnetic radiation, gravitational waves, and neutrinos, are combined to provide a more complete picture of astrophysical phenomena. For example, the detection of gravitational waves from neutron star mergers has been complemented by the observation of gamma rays and X-rays from the same events, revealing the complex interactions that occur during these cataclysmic collisions. Pulsars, as the remnants of such mergers, provide a critical link in this chain of discovery, helping scientists understand the life cycles of stars and the mechanisms that drive some of the universe's most energetic processes. As we look to the future, the possibilities for pulsar research are virtually limitless. With the advent of next-generation telescopes like the Square Kilometre Array, we are poised to uncover tens of thousands of new pulsars, including those hidden in the dense stellar environments of globular clusters and the galactic center. These discoveries will provide unprecedented opportunities to study pulsars in a wide range of environments, from the outskirts of galaxies to the crowded regions near supermassive black holes. In addition, advances in X-ray and gamma-ray astronomy will allow us to probe the high-energy processes that power pulsars and their magnetospheres in greater detail. Instruments like Athena, the Cherenkov Telescope Array, and proposed missions such as the Lynx X-ray Observatory will provide the sensitivity and resolution needed to study pulsars at the smallest scales, revealing the inner workings of these cosmic engines. The study of pulsars is not just about understanding the stars themselves, it is about unlocking the secrets of the universe. From their role in testing the fundamental laws of physics to their potential as tools for interstellar navigation, pulsars are windows into a world of extreme possibilities. They challenge us to think beyond the boundaries of our knowledge and to embrace the wonder and complexity of the cosmos. Pulsars remind us that the universe is a place of infinite curiosity and discovery. They are beacons of knowledge, guiding us toward a deeper understanding of the forces that shape our reality. As we continue to explore these enigmatic objects, we are not only expanding our understanding of the cosmos but also reaffirming our place within it, a place defined by curiosity, exploration, and the unyielding pursuit of knowledge. And in their steady, rhythmic pulses, we find not just the echoes of dying stars but the heartbeat of the universe itself. Pulsars are more than remnants of cosmic destruction, they are the silent yet commanding storytellers of the universe, drawing us into their orbit with mysteries as deep as space itself. They force us to confront questions that lie at the edge of human understanding, acting as keys to unlock the secrets of time, space, and even the origin of matter. What else might these enigmatic objects reveal? The answers could rewrite the story of the cosmos. One of the most mind-bending aspects of pulsars is their relationship to spacetime itself. Imagine a fabric so distorted by a pulsar's immense gravity that time moves differently near its surface. These distortions are not theoretical, they are measurable. In binary pulsar systems, where a pulsar orbits another star, the warping of spacetime causes the orbit to slowly decay, emitting gravitational waves as predicted by Einstein's theory of general relativity. These ripples in spacetime carry information not just about the pulsar but about the very nature of gravity itself. Every gravitational wave we detect is a message from the depths of the universe, a whisper from events billions of years in the making. But pulsars don't just test our understanding of gravity, they challenge us to rethink the building blocks of matter. Neutron stars are so dense that their interiors might contain exotic forms of matter that exist nowhere else in the universe. Some theories suggest that deep within their cores, the neutrons themselves break down into a sea of quarks, the fundamental particles that make up protons and neutrons. This quark-gluon plasma might hold clues to conditions that existed moments after the Big Bang. Could pulsars be relics not only of dying stars but also of the universe's fiery birth? The story of pulsars grows even stranger when we consider the possibility of strange stars. These are hypothetical neutron stars that have transformed entirely into strange matter, a theorized state where quarks combine in ways we've never observed. If strange stars exist, they would be among the most stable objects in the universe, and they might even emit unique signals, waiting to be uncovered by our telescopes. The discovery of a strange star would revolutionize our understanding of particle physics and force us to rewrite the rules of what is possible in the universe. Even the outermost layers of pulsars defy comprehension. Their surfaces are believed to be covered by a nuclear crust, a lattice of nuclei so tightly packed that it's stronger than any material on Earth. Beneath this crust lies a sea of neutrons, where matter behaves like a fluid under unimaginable pressure. As the pulsar spins, this crust occasionally cracks under the strain, causing starquakes. These quakes release bursts of energy so intense they can outshine entire galaxies for brief moments. Each quake is a reminder that even the most stable-looking objects in the universe are constantly in flux, their surfaces rippling with the echoes of their chaotic births. And then there are the pulsar beams, those mighty lighthouses that sweep through the cosmos. What powers them? Scientists believe these beams are driven by the interaction between the pulsar's intense magnetic field and its rapid rotation. As charged particles are accelerated along the magnetic poles, they emit radiation across the electromagnetic spectrum. But this model is far from complete. Why do some pulsars emit primarily radio waves, while others glow in gamma rays? Why do some pulsars flicker unpredictably, while others pulse with perfect precision? These questions hint at complexities in the pulsar engine that we are only beginning to understand. The beams themselves may also carry hidden messages. Researchers have discovered that some pulsars exhibit strange, quasi-periodic changes in their pulse timing and intensity. These variations could be caused by phenomena as mundane as changes in the pulsar's magnetic field, or as exotic as interactions with dark matter. Could the signals from pulsars hold clues to one of the greatest mysteries of modern science, the nature of the invisible matter that makes up most of the universe? Some scientists speculate that dark matter particles, if they exist, might accumulate in pulsars, subtly altering their behavior in ways that we could detect. If true, pulsars could become the universe's natural laboratories for probing this elusive substance. Pulsars also link us to the distant past and the far future. The precision of their timing allows astronomers to measure the movements of entire star systems and even galaxies. By observing pulsars, we can reconstruct the history of the Milky Way, tracing the paths of stars that formed billions of years ago. Pulsars also offer a glimpse of the universe's distant future, as they slowly lose energy and fade into zombie stars that persist as cold, dark remnants for trillions of years. What role might these eternal objects play in the endgame of the cosmos? Could they become the final witnesses to the universe's slow heat death, or might they harbor the seeds of new creation in some unknown process? Beyond their astrophysical significance, pulsars provoke deeper, almost philosophical questions about the nature of time and existence. A pulsar's spin represents the most precise clockwork nature can produce, yet it is inexorably slowing down, its energy bleeding away into the void. This interplay between permanence and impermanence mirrors the universe itself, a place where the unyielding laws of physics govern a cosmos in constant motion, forever changing and evolving. Pulsars remind us that even in the face of cosmic decay, there is beauty in endurance and precision, in the way these lighthouses persist against the vast indifference of space. And yet, for all their precision, pulsars hold surprises. Some emit sporadic bursts of radio waves that seem to defy their regular rhythms. Others suddenly change their spin rate, as if shifting gears in response to some unseen force. These phenomena, known as nulling and intermittent pulsars, hint at processes we don't yet understand. Could these irregularities be clues to deeper layers of physics, or are they simply artifacts of a chaotic universe? Every time we think we've solved the puzzle of pulsars, they present us with new riddles. The future of pulsar research promises to be as thrilling as its past. Advanced observatories like the Square Kilometre Array will allow us to detect faint pulsars hidden in the most extreme environments, near black holes, in dense star clusters, or even in other galaxies. These discoveries could lead to entirely new classes of pulsars, each with their own unique behaviors and secrets. Space-based detectors, like the proposed ELISA mission, will complement this work by observing the gravitational waves emitted by pulsar mergers, revealing the violent events that shape the cosmos. Pulsars also hold the potential to revolutionize space exploration. Their predictable signals make them ideal navigation beacons for spacecraft venturing into deep space. NASA has already tested this concept with the NICER experiment, which demonstrated that pulsars could be used to pinpoint the position of a spacecraft anywhere in the galaxy. In the future, interstellar probes could navigate the stars using nothing but the rhythmic pulses of these distant lighthouses, making pulsars not just objects of study but partners in humanity's journey to the stars. In the end, pulsars are more than astronomical objects, they are symbols of the universe's resilience and ingenuity. Born from cataclysmic destruction, they emerge as engines of precision and power, bridging the gap between the macroscopic and the quantum, the ancient past and the distant future. They remind us that even in the aftermath of cosmic death, there is beauty, order, and purpose. As we continue to unlock their secrets, we are reminded of the boundless curiosity that defines us as a species, and the infinite wonders that await in the vast expanse of the cosmos. The study of pulsars is not just an exercise in observation but a deep dive into the fundamental forces and phenomena that shape the universe. These rotating neutron stars act as natural laboratories where conditions are so extreme that they allow us to test theories and conduct experiments that would be impossible to replicate on Earth. Every pulsar is a unique experiment, a cosmic machine whose behavior reveals the interplay of gravity, electromagnetism, quantum mechanics, and nuclear physics. One of the most captivating areas of research is the role of pulsars in detecting and characterizing gravitational waves. While instruments like LIGO and Virgo detect high-frequency gravitational waves from catastrophic events such as neutron star or black hole mergers, pulsars provide access to an entirely different frequency range, nanohertz gravitational waves. These waves are thought to be produced by supermassive black hole binaries orbiting each other in distant galaxies. To detect them, astronomers rely on pulsar timing arrays, PDAs, networks of precisely monitored millisecond pulsars distributed across the sky. Subtle variations in the arrival times of their pulses can reveal the passage of gravitational waves, stretching and compressing spacetime across vast cosmic distances. Recent breakthroughs in PTA research have already hinted at a gravitational wave background, a faint hum created by the combined signals of countless supermassive black hole binaries. This discovery is a milestone in understanding how galaxies evolve, merge, and grow over billions of years. Future studies could even map the locations of these binaries, offering unprecedented insights into the large-scale structure of the universe. Pulsars also help us study the behavior of matter under extreme densities. Neutron stars are so compact that a single sugar cube-sized piece of their material would weigh about 1 billion tons on Earth. The forces at work inside a neutron star compress matter to such an extent that atomic nuclei dissolve, leaving a sea of neutrons and possibly other exotic particles. Theorists have proposed that neutron stars might host quark matter or strange matter, states of matter composed of free quarks, or even strange quarks, a heavier cousin of the more familiar up and down quarks. To understand these possibilities, scientists rely on observations of pulsar mass and radius. The most massive neutron stars ever discovered, such as PSR J0740 plus 6620, challenge existing models of the equation of state, EOS, which describes how matter behaves under extreme pressure. Observations with instruments like NICER, Neutron Star Interior Composition Explorer, have provided precise measurements of pulsar radii, helping to constrain the EOS and refine our understanding of neutron star interiors. These studies not only probe the fundamental forces at work in the universe but also test our theories of particle physics under conditions unattainable in any laboratory. One of the most striking features of pulsars is their magnetic fields, which are trillions of times stronger than Earth's. These fields are responsible for the spectacular phenomena we associate with pulsars, including their beams of electromagnetic radiation. In magnetars, a subclass of neutron stars, the magnetic fields can reach up to 10 superscript 1 Gauss, creating some of the most violent environments in the universe. Magnetar flares can release as much energy in a fraction of a second as the Sun emits in 100,000 years, disrupting satellites and ionizing Earth's atmosphere even from thousands of light-years away. Recent studies have shown that these magnetic fields may decay over time, powering the X-ray and gamma-ray emissions observed from magnetars. This decay process, driven by the movement of charged particles within the neutron star, provides a unique opportunity to study the interaction between magnetism, matter, and radiation in extreme environments. Understanding these processes could have profound implications for our knowledge of magnetic fields on all scales, from planets to galaxies. Pulsars are also crucial for studying the interstellar medium, ISM, the vast expanse of gas, plasma, and dust that fills the space between stars. As the radio waves emitted by pulsars travel through the ISM, they interact with the charged particles in their path, causing effects like dispersion and scattering. By analyzing these effects, astronomers can map the density, composition, and structure of the ISM across the Milky Way. This work has revealed phenomena such as vast ionized regions around massive stars and turbulent filaments of gas shaped by supernova explosions. Pulsar observations are even helping to study the mysterious missing baryon problem, the search for the ordinary matter that seems to be unaccounted for in the universe. Another exciting development in pulsar research is the study of pulsar glitches, sudden changes in their rotation rates. These glitches are thought to result from interactions between the solid crust and the superfluid interior of the neutron star. In a superfluid, matter flows without friction, a property that arises from quantum mechanics. Glitches occur when the superfluid's angular momentum transfers to the crust, causing the pulsar's spin rate to increase abruptly. By studying these glitches, scientists are gaining valuable insights into the strange and exotic physics of superfluidity and how it operates under extreme conditions. Fast radio bursts, FRBs, a recently discovered phenomenon, have added a new layer of intrigue to the study of neutron stars. These millisecond-long bursts of intense radio waves are thought to originate from highly magnetized neutron stars, possibly magnetars, located in distant galaxies. Some FRBs exhibit repeating patterns, suggesting complex magnetospheric activity or interactions with surrounding material. The discovery of FRBs associated with magnetar-like bursts has strengthened the connection between these enigmatic signals and the extreme physics of neutron stars. The hunt for new pulsars continues to push the boundaries of what we know. Modern radio surveys, powered by telescopes like the Meerkat Array and the upcoming Square Kilometre Array, are uncovering pulsars in previously inaccessible regions, such as the dense cores of globular clusters and the crowded areas near the galactic center. These discoveries are shedding light on the population and distribution of pulsars, revealing trends in their birth and evolution. But pulsars do not merely exist as objects of study, they are also tools for exploration. One of the most promising applications of pulsar research is in navigation. Their regular pulses make them ideal beacons for spacecraft, offering a natural alternative to GPS for interstellar travel. This concept, known as pulsar-based navigation, has already been demonstrated in principle by NASA's NICER mission, which used X-ray signals from pulsars to determine the position of the International Space Station with remarkable accuracy. In the future, pulsars could guide humanity's exploration of the galaxy, providing a universal map etched into the fabric of spacetime. As we delve deeper into the mysteries of pulsars, we are reminded of the interconnectedness of the universe. These spinning remnants of stars not only illuminate the life cycles of massive stars but also provide clues about the origins of matter, the nature of gravity, and the evolution of galaxies. They bridge the gap between the microscopic and the cosmic, offering insights into everything from the behavior of subatomic particles to the dynamics of galaxy clusters. In their relentless, rhythmic pulses, pulsars whisper the secrets of the universe across vast distances and unfathomable timescales. They are cosmic witnesses to the birth, death, and rebirth of stars, carrying the echoes of creation itself. As our technology improves and our understanding deepens, we stand on the brink of unlocking even greater mysteries, guided by the steady light of these extraordinary cosmic lighthouses. The ongoing exploration of pulsars continues to redefine the boundaries of astrophysics, unraveling mysteries that challenge our understanding of the universe and inspiring new lines of inquiry. These extraordinary celestial objects act as beacons that not only guide our knowledge of star evolution but also serve as tools to probe the very fabric of spacetime, the behavior of matter under extreme conditions, and the hidden forces shaping the cosmos. One of the most fascinating aspects of pulsar research lies in their ability to act as cosmic probes. As radio waves emitted by pulsars traverse the vast expanses of space, they interact with the interstellar medium, ISM, in unique ways. This interaction leaves measurable imprints on the pulsar signals, such as dispersion, a delay in signal arrival due to the frequency-dependent effects of the ISM, and scattering, causing signal broadening or smearing. By analyzing these effects, astronomers can reconstruct detailed maps of the ISM's density, temperature, magnetic field structure, and composition across the Milky Way. These ISM studies have led to groundbreaking discoveries, such as the detection of turbulence within giant molecular clouds and the identification of hot ionized gas bubbles surrounding massive stars. By mapping these structures, scientists are uncovering how supernova explosions and stellar winds shape the galaxy, influencing the formation of future stars and planets. Pulsars, in essence, become tools for tracing the dynamic processes that govern the life cycle of the Milky Way. Pulsars also provide a direct link to the mysteries of magnetism on cosmic scales. Their magnetic fields, which are trillions of times stronger than those found on Earth, give rise to some of the most energetic phenomena in the universe. These fields accelerate particles to nearly the speed of light, creating intense beams of radiation and driving pulsar wind nebulae, expanding clouds of charged particles glowing in X-rays and gamma rays. The Crab Nebula, one of the most studied pulsar wind nebulae, continues to fascinate scientists as they investigate the mechanisms that generate its spectacular emission and intricate filamentary structures. Even more extreme are magnetars, pulsars with magnetic fields up to 10 superscript 1 Gauss. These fields are so powerful that they can distort the atomic structure of matter, breaking apart atoms and molecules. Magnetars periodically release gigantic bursts of energy known as soft gamma repeaters or giant flares. These events are so intense that, in rare cases, they can even affect Earth, disrupting satellite communications and ionizing the upper atmosphere. By studying magnetar outbursts, scientists are gaining insight into the physics of magnetic reconnection, a process that releases magnetic energy explosively and plays a key role in phenomena such as solar flares and auroras. The connection between pulsars and fast radio bursts, FRBs, has added yet another dimension to this field of research. While FRBs were initially detected as mysterious, millisecond-long bursts of radio waves from unknown sources, recent observations have linked some of these bursts to magnetars. This connection suggests that extreme magnetic fields and plasma environments around neutron stars might be responsible for generating FRBs. However, many FRBs remain enigmatic, with their origins and mechanisms of production still under debate. Some theories even suggest that certain FRBs could be signals from highly magnetized environments around black holes or from yet undiscovered exotic astrophysical phenomena. Another frontier in pulsar research is the study of their timing precision. Pulsars, particularly millisecond pulsars, are nature's most accurate clocks, with some maintaining a level of regularity that rivals atomic clocks. This remarkable stability allows scientists to use pulsars as tools for fundamental tests of physics. For example, the timing of pulsars in binary systems enables the precise measurement of their orbits, revealing effects predicted by general relativity, such as gravitational wave emission and time dilation. The Hulse-Taylor binary pulsar, PSRB 1913+16, provided the first indirect evidence for gravitational waves and earned its discoverers the Nobel Prize in Physics in 1993. The precision of pulsar timing also makes them indispensable in the search for gravitational waves from supermassive black hole binaries. These systems, formed when galaxies merge, emit low-frequency gravitational waves that ripple across spacetime. By monitoring an array of millisecond pulsars, collectively called a pulsar timing array, PDA, scientists can detect tiny distortions in spacetime caused by these waves. Recent data from PDAs, including the European Pulsar Timing Array, EPTA, and the North American Nanohertz Observatory for Gravitational Waves, NNOGRAV, have provided tantalizing evidence for the presence of a gravitational wave background, offering a new window into the processes that drive galaxy evolution. Beyond their astrophysical significance, pulsars are proving to be invaluable in the study of fundamental forces and particles. Neutron stars contain some of the densest matter in the universe, making them ideal laboratories for testing the behavior of matter at extreme densities. Theorists are investigating whether pulsars could harbor exotic forms of matter, such as quark matter or strange matter. These states involve quarks, elementary particles that make up protons and neutrons, existing freely rather than confined within particles. Detecting evidence of such matter would revolutionize our understanding of the strong nuclear force, one of the fundamental forces governing the universe. Some researchers even speculate that pulsars could provide clues to the nature of dark matter, the mysterious substance that makes up about 27% of the universe. Dark matter particles, if they interact with ordinary matter, could accumulate inside neutron stars, altering their observable properties. For example, the presence of dark matter could affect a pulsar's rotation rate, magnetic field, or thermal emission. By studying these effects, astronomers hope to uncover indirect evidence for dark matter, potentially solving one of the greatest mysteries in modern physics. The search for new pulsars is continually expanding, driven by advancements in technology and observational techniques. The Square Kilometre Array, SKA, the most ambitious radio telescope project ever conceived, is set to revolutionize pulsar astronomy. With its unprecedented sensitivity, the SKA is expected to discover tens of thousands of new pulsars, including rare objects in unexplored regions of the galaxy. These discoveries will provide an unparalleled opportunity to study the population, distribution, and evolution of pulsars across the Milky Way. In addition to ground-based telescopes, space-based observatories are playing an increasingly important role in pulsar research. Missions like the Fermi Gamma Ray Space Telescope and NICER have expanded our view of pulsars beyond the radio spectrum, revealing populations of gamma-ray pulsars and X-ray emitting neutron stars. Future missions, such as the proposed Lynx X-ray Observatory, aim to probe the high-energy universe with even greater sensitivity, unlocking new insights into the extreme physics of pulsars and their environments. Pulsars also hold promise for the future of space exploration. Their predictable signals make them ideal candidates for interstellar navigation. By triangulating signals from multiple pulsars, spacecraft could determine their position and velocity anywhere in the galaxy with remarkable accuracy. This concept, known as pulsar-based navigation, has already been demonstrated in principle and could become a cornerstone of future interstellar missions. Ultimately, pulsars are far more than relics of dead stars, they are windows into the deepest mysteries of the universe. From their role in testing the fundamental laws of physics to their potential as tools for mapping the cosmos, pulsars are at the forefront of discovery, guiding us toward a deeper understanding of the cosmos and our place within it. As we continue to study these extraordinary objects, we are not only unraveling the secrets of the universe but also uncovering new questions, ensuring that the story of pulsars, and our fascination with them, will endure for generations to come. Pulsars are, quite simply, among the most profound astrophysical discoveries of the modern era. They embody a paradox of extremes, objects so small yet so powerful, so ancient yet so precise, and so far away yet so intimately connected to the forces that shape the universe. As we push forward in pulsar research, the questions they raise deepen, becoming more intricate and entangled with some of the universe's greatest mysteries. One of the emerging areas of study is the role of pulsars in the birth and evolution of stellar systems. When a massive star explodes as a supernova, the pulsar that remains can either be isolated or part of a binary system. In binary systems, the interactions between the pulsar and its companion star are particularly fascinating. Over time, the pulsar may accrete material from its companion, forming an accretion disk and spinning up to become a millisecond pulsar. This process, sometimes referred to as recycling, creates some of the fastest spinning pulsars we know, with rotational speeds exceeding 700 revolutions per second. These systems provide unique opportunities to study the transfer of angular momentum and the physics of mass exchange in extreme gravitational environments. Moreover, binary pulsars are essential tools for studying general relativity. Systems like the double pulsar, PSR J0737-3039, where two pulsars orbit each other, allow for precise measurements of relativistic effects. In such systems, phenomena like gravitational time dilation, orbital decay due to gravitational wave emission, and Shapiro delay, caused by the curvature of spacetime near massive objects, can be directly observed. These observations not only confirm the predictions of general relativity but also provide constraints on alternative theories of gravity, helping refine our understanding of the fundamental forces of nature. The link between pulsars and black holes is another tantalizing avenue of research. While no pulsar has yet been observed in orbit around a black hole, such a discovery would represent a major breakthrough. A pulsar black hole binary would allow scientists to test the limits of general relativity in the strongest gravitational fields possible. Observing the pulsar's timing signals as it orbits the black hole could reveal intricate details about spacetime near the event horizon, including potential deviations from Einstein's predictions. The search for such systems is ongoing, with large-scale pulsar surveys combing the sky for this elusive pairing. Pulsar timing is also being used to probe the distribution of dark matter in the galaxy. Dark matter, which does not emit or absorb light, reveals its presence only through its gravitational effects. By analyzing the motion of pulsars within the Milky Way, astronomers can infer the distribution of dark matter in the galaxy's halo. Pulsars in globular clusters or near the galactic center are particularly valuable for this purpose, as these regions are expected to have high concentrations of dark matter. These studies not only enhance our understanding of pulsars but also contribute to the broader effort to unravel the nature of dark matter, one of the most enduring mysteries of modern astrophysics. Another exciting application of pulsar research is the use of their signals to detect cosmic phase transitions. In the early universe, as it expanded and cooled, it likely underwent several phase transitions, moments when the fundamental forces of nature, such as the strong and weak nuclear forces, separated or changed behavior. These transitions may have generated gravitational waves, leaving imprints on spacetime that persist to this day. Pulsar timing arrays, by monitoring the precise timing of millisecond pulsars, could detect these relic waves, providing a glimpse into the universe's earliest moments, less than a fraction of a second after the Big Bang. The detection of fast radio bursts, FRBs, has added another layer of complexity to the study of neutron stars. While some FRBs have been definitively linked to magnetars, others remain mysterious, with no clear connection to known astrophysical objects. Some FRBs exhibit strange periodic patterns, suggesting highly organized processes, while others are completely random. The discovery of repeating FRBs adds further intrigue, raising questions about whether they are produced by young, highly magnetized neutron stars, collisions, or entirely new astrophysical phenomena. Pulsars and magnetars provide a natural connection to FRBs, as their extreme magnetic fields and dynamic environments are capable of producing the short, intense bursts of radio energy that define FRBs. As we probe deeper into pulsar environments, we are beginning to uncover their role in particle acceleration. Pulsars are natural particle accelerators, capable of driving particles to energies far beyond those achieved in Earth-based experiments like the Large Hadron Collider. The charged particles ejected in pulsar winds interact with magnetic fields to produce high-energy radiation, including X-rays and gamma rays. Observing these emissions not only provides insights into the physics of particle acceleration but also helps us understand the origin of cosmic rays, the high-energy particles that bombard Earth's atmosphere from space. On an even larger scale, pulsars contribute to the broader study of galaxy dynamics. Their distribution across the Milky Way reveals patterns of star formation, supernova activity, and the movement of stellar populations over billions of years. Pulsars in globular clusters, dense collections of ancient stars, provide clues about the conditions in these environments and the processes that lead to the formation of compact objects. Meanwhile, pulsars in the galactic halo offer insights into the history of the Milky Way's formation and its interactions with neighboring galaxies. The study of pulsars is also expanding beyond our galaxy. With the increasing sensitivity of modern telescopes, astronomers are beginning to detect pulsars in other galaxies, including the Magellanic Clouds and even the Andromeda Galaxy. These extragalactic pulsars provide a unique perspective on how neutron stars form and evolve in different environments, from metal-poor galaxies to starburst regions where supernovae are more frequent. Looking ahead, the future of pulsar research is brighter than ever. The Square Kilometre Array, SKA, set to begin operations in the coming years, will revolutionize our ability to study pulsars, potentially discovering tens of thousands of new ones. The SKA's unprecedented sensitivity will allow scientists to explore the faintest and most distant pulsars, uncovering rare types such as intermittent pulsars that switch on and off unpredictably or nulling pulsars that occasionally stop emitting altogether. Space-based missions, like the proposed Lynx X-ray Observatory and the Laser Interferometer Space Antenna, LISA, will complement these efforts by studying the high-energy emissions from pulsars and detecting gravitational waves from neutron star mergers, respectively. These tools will provide a multi-messenger view of pulsars, combining electromagnetic observations with gravitational wave data to create a more complete picture of their behavior and interactions. In the grand tapestry of the universe, pulsars are threads that connect the smallest particles to the largest structures, from quarks to galaxies. They are reminders of the cosmic violence that creates them, the precision that governs their signals, and the mysteries they continue to hold. As we study pulsars, we are not only exploring the nature of stars and matter but also uncovering the deep connections that bind the universe together. Every pulse carries the echo of its creation, a message from a distant corner of the cosmos that invites us to listen, to learn, and to discover. The journey of pulsar research is far from over, and with each new discovery, we step closer to answering the most profound questions about our universe and our place within it. The story of pulsars is one of perpetual discovery, where every new observation and theory unlocks deeper layers of the cosmos. These enigmatic remnants of massive stars continue to challenge our understanding of physics, revealing phenomena that stretch the limits of human knowledge. As the pace of research accelerates, pulsars are emerging as a focal point for some of the most ambitious scientific endeavors in history. One of the most intriguing aspects of pulsars is their potential to probe the laws of quantum physics under extreme conditions. Deep within the cores of neutron stars, matter is compressed to densities billions of times greater than those found on Earth. At these densities, the behavior of particles is governed by quantum mechanics, yet this realm remains largely uncharted. Pulsars offer a unique opportunity to study the interplay between quantum physics and gravity, two of the most fundamental forces in the universe, which are notoriously difficult to reconcile in a unified framework. In particular, the interiors of neutron stars may contain exotic states of matter that challenge current models of particle physics. Some theories suggest that the cores of the most massive neutron stars could collapse into quark matter, a state where protons and neutrons break apart into their constituent quarks. Even more exotic is the possibility of strange matter, composed of strange quarks, which could be more stable than normal atomic matter. If pulsars harbor such materials, their discovery would revolutionize our understanding of the strong nuclear force, the force that binds quarks together in atomic nuclei. Observations of pulsar masses and radii, combined with sophisticated simulations, are helping to constrain these possibilities, pushing the boundaries of what we know about the fundamental building blocks of matter. Beyond their interiors, pulsars exhibit extraordinary magnetic fields that remain poorly understood. These fields are generated during the formation of the neutron star, amplified as the star collapses into a highly compact object. In magnetars, the most extreme type of pulsar, these magnetic fields can reach strengths of 10^1 Gauss, powerful enough to deform atomic structures and generate catastrophic outbursts of energy. Magnetar flares are among the most violent events in the universe, capable of releasing more energy in a single second than the sun emits in 100,000 years. These flares produce intense gamma-ray and X-ray emissions, and studying them provides insights into the processes of magnetic reconnection and particle acceleration, phenomena that also occur on much smaller scales in our own Sunday magnetars may also hold the key to understanding fast radio bursts, FRBs. Mysterious millisecond-long bursts of radio waves that have puzzled astronomers since their discovery in 2007. Recent observations have linked some FRBs to magnetars, suggesting that their intense magnetic fields and dynamic environments could produce the energetic phenomena needed to generate these bursts. However, the exact mechanism remains unclear, and many FRBs, especially those originating from distant galaxies, exhibit behaviors that defy simple explanations. Could there be other types of neutron stars or entirely new astrophysical objects responsible for these signals? The connection between pulsars, magnetars, and FRBs remains one of the most tantalizing open questions in modern astrophysics. Pulsars also offer a unique window into the study of gravitational waves, ripples in spacetime produced by some of the most dramatic events in the universe. While detectors like LIGO and Virgo are designed to capture high-frequency gravitational waves from sources like black hole and neutron star mergers, pulsars allow us to study low-frequency gravitational waves from supermassive black hole binaries. Pulsar timing arrays, PDAs, which monitor the precise timing of millisecond pulsars across the sky, are sensitive to these slow, long-wavelength waves. By analyzing tiny variations in the arrival times of pulsar signals, astronomers can detect the subtle distortions caused by gravitational waves passing through our galaxy. Recent results from PDAs have provided tantalizing hints of a gravitational wave background, a faint chorus produced by countless merging supermassive black holes across the universe. The potential of pulsar-based navigation is another exciting frontier. Pulsars' precise and regular signals make them natural beacons for determining position and velocity in space, far beyond the reach of Earth-based systems like GPS. This concept, known as XNAV, X-ray navigation, has already been tested with NASA's NICER experiment, which demonstrated the feasibility of using pulsar signals to locate the International Space Station in orbit. In the future, pulsar-based navigation could guide spacecraft on interstellar missions, providing humanity with a galactic positioning system that operates independently of any planetary infrastructure. The search for new pulsars continues to uncover unexpected phenomena. Advanced radio telescopes, such as the Square Kilometre Array, SKA, and the Meerkat Array, are discovering pulsars in extreme environments, including the dense cores of globular clusters and the crowded regions near the galactic center. These discoveries are shedding light on the formation and evolution of pulsars, as well as the dynamics of the dense stellar populations in which they reside. The SKA, in particular, is expected to revolutionize our understanding of pulsars, potentially increasing the known population by an order of magnitude and revealing rare and exotic types of neutron stars that have so far eluded detection. Space-based observatories are also expanding the horizons of pulsar research. The Fermi Gamma-ray Space Telescope has uncovered a population of gamma-ray pulsars, many of which were invisible in the radio spectrum. These discoveries highlight the diversity of pulsar emission mechanisms and suggest that there may be entire classes of neutron stars yet to be identified. Proposed missions like the Lynx X-ray Observatory and the Cherenkov Telescope Array will further enhance our ability to study high-energy emissions from pulsars and their environments, offering new insights into the physics of particle acceleration and magnetic field dynamics. Even as we expand our observational capabilities, theoretical research is advancing in parallel, driving new insights into pulsar behavior. Simulations of neutron star mergers, for example, are revealing the complex interplay of gravity, magnetism, and nuclear physics that occurs during these cataclysmic events. These models are helping scientists interpret observations of kilonovae, the brilliant flashes of light produced by neutron star collisions, and the gravitational waves they emit. Such studies are not only shedding light on the formation of heavy elements like gold and platinum but also providing clues about the birth of new pulsars in the aftermath of these mergers. As we look to the future, the possibilities for pulsar research are as vast as the cosmos itself. These objects, born in the explosive deaths of massive stars, continue to illuminate the fundamental forces that govern the universe. From their role in testing the limits of general relativity to their potential as tools for interstellar exploration, pulsars are shaping our understanding of the cosmos in ways that were unimaginable just a few decades ago. Pulsars remind us that the universe is not static or predictable but a dynamic, evolving tapestry of matter, energy, and forces. They are the cosmic witnesses to events that have shaped galaxies, stars, and even the elements that make up life on Earth. As we continue to study these extraordinary objects, we are not only uncovering the secrets of the universe but also deepening our understanding of our place within it. Each pulse from a distant neutron star carries with it a message, a testament to the resilience of matter and the unyielding march of time across the vast expanse of space. In the end, pulsars are far more than just cosmic lighthouses. They are the ultimate paradox, remnants of catastrophic destruction, yet symbols of order and precision, ancient relics of stellar death, yet gateways to the future of science and exploration. Their study connects us to the most fundamental questions about the universe: how it began, how it evolved, and where it is heading. Each discovery about pulsars pulls back the curtain on the workings of reality itself, revealing the hidden dynamics of gravity, matter, energy, and spacetime. These enigmatic objects challenge us to confront the extremes. Their dense interiors harbor mysteries about the building blocks of matter, where the physics of atomic nuclei collapses into something new and exotic, something we have yet to fully comprehend. Their magnetic fields, so unimaginably powerful that they could distort the very atoms in our bodies, show us forces operating at scales that strain the limits of current science. Their relentless pulses, some spinning hundreds of times per second with atomic clock precision, are a reminder of the universe's capacity for order amid chaos. Pulsars are also storytellers, preserving the history of the cosmos in their timing, their location, and their behavior. They tell the tale of the violent lives of stars, the evolution of galaxies, and the interstellar medium that lies between. They show us how matter behaves when pushed to its absolute limits, how stars die, and how they continue to shape their surroundings long after their fiery end. Through their beams, they carry messages across the void, information that speaks to the interconnectedness of everything in the universe, from the microscopic quantum scale to the gravitational dance of entire galaxies. But perhaps most profoundly, pulsars inspire us to look outward and dream of what is possible. They have become tools of exploration, guiding us in our attempts to map the unseen forces that shape the universe. Their signals are being repurposed to navigate the stars, paving the way for humanity's future beyond Earth. They stand as cosmic milestones, marking humanity's ability to unlock the secrets of the universe with ingenuity, curiosity, and persistence. As we gaze deeper into the cosmos with ever more powerful instruments, pulsars will remain at the forefront of discovery. The next generation of telescopes, like the Square Kilometre Array, promises to uncover pulsars in far-flung corners of the galaxy and even in other galaxies, bringing new insights into the physics of neutron stars and their environments. Space-based observatories will reveal their high-energy secrets, allowing us to study the forces that drive their incredible emissions and perhaps even uncover entirely new classes of objects. The search for pulsars also pushes the boundaries of technology and computation. Advanced machine learning algorithms are already discovering pulsars hidden in vast datasets, uncovering faint signals that human eyes would never see. As our computational power grows, so will our ability to find and analyze pulsars, uncovering more of their secrets and opening new doors to understanding the universe. Ultimately, pulsars are not just astrophysical phenomena, they are mirrors of human ambition and ingenuity. They show us the power of asking questions, of looking beyond what we know, and of reaching for the unknown. They are reminders of the universe's capacity for both destruction and creation, for chaos and precision, and for revealing truths that transcend the boundaries of time and space. The pulsars we study today are ancient, their origins stretching back billions of years, but their significance will carry forward into the future. As we continue to explore and learn from them, we are participating in a journey that connects us to the stars and to the deepest mysteries of existence. Pulsars, in their steady, rhythmic pulses, remind us of the vastness of the universe, the resilience of matter, and the boundless potential of human curiosity. Their light will guide us, not just through the cosmos, but toward the answers to the questions that define our place in the universe. At the heart of our Milky Way lies a mystery cloaked in silence and shadow, a gravitational abyss known as Sagittarius A*, a supermassive black hole more than 4 million times the mass of our Sun. Though invisible to the eye, it governs the motion of stars and gas clouds in the galactic center, orchestrating a cosmic dance with overwhelming gravity. Stars near it, such as S2, race around at speeds surpassing 7,000 kilometers per second, completing orbits in mere decades, a blink in cosmic time. These stellar orbits provide some of the strongest evidence for the existence of an object so compact and massive that no known force could support it against collapse. Despite its immense influence, Sagittarius A* is eerily quiet compared to the active hearts of other galaxies. It occasionally flares with X-ray and radio emissions, subtle whispers of matter being consumed at its edge. This subdued activity makes it an ideal laboratory for testing Einstein's theory of general relativity in the extreme. Observations with radio telescopes, including the Event Horizon Telescope, have begun to pierce the veil around it, revealing a shadow-like ring, a silhouette cast by warped light bending around the event horizon. Surrounding this dark monolith is a region filled with turbulent gas, star formation, and enigmatic structures like the radio arc and the mysterious Fermi bubbles extending far above and below the galactic plane. These phenomena suggest that Sagittarius A* was not always so silent. In the past, it may have awakened in a storm of radiation, possibly shaping the environment of our galaxy on grand scales. Understanding the behavior of matter and light near Sagittarius A* doesn't just tell us about the Milky Way, it opens a window into the fundamental workings of the universe. Black holes stretch the fabric of spacetime, slow down time near their boundaries, and challenge the limits of physics. The closer we look, the more the ordinary laws of nature begin to falter. It is here, in this hidden core of our galaxy, that nature plays by rules we still struggle to fully comprehend. To peer into the realm of Sagittarius A* is to approach the very edge of what is physically possible. The black hole itself is surrounded by a region known as the event horizon, the point of no return, where gravity becomes so intense that not even light can escape. But this isn't just a boundary. It's a limit beyond which the known laws of physics dissolve into speculation. What lies beyond the horizon is unknown. A singularity? A bridge to another universe? Or something far stranger? Despite its invisibility, the influence of Sagittarius A* extends across thousands of light-years. Its gravity shepherds stars into tight orbits and may even help regulate the rate of star formation throughout the galaxy. As stars are pulled inward or disrupted, their material can be stretched and heated, creating spectacular bursts of radiation, brief but powerful echoes of cosmic consumption. Yet, these outbursts are rare. Sagittarius A* now appears to slumber, its feeding rate so low that it radiates less energy than a single household light bulb per unit mass. And yet, the quiet is deceptive. Evidence from surrounding structures hints at a violent past. The enormous Fermi bubbles, twin lobes of high-energy gas stretching tens of thousands of light-years, may be the fossil remains of an ancient outburst. Perhaps millions of years ago, Sagittarius A* blazed as a quasar, a beacon bright enough to outshine the rest of the galaxy. That light, long extinguished, may have rippled through the galactic medium, heating and shaping gas flows still visible today. More recently, astronomers have begun detecting ripples and flares from Sagittarius A* that arrive unpredictably, flashing in infrared or X-ray bands. These are likely caused by small clumps of matter, perhaps disrupted asteroids or wandering gas clouds, brushing too close to the event horizon. They spiral inward, heat up, and vanish. One such gas cloud, known as G2, was once thought to be on a collision course with the black hole, but it survived the encounter, a reminder of how much we still have to learn. The environment around Sagittarius A* is chaotic and extreme. Magnetic fields twist and tangle in invisible threads, and radiation bathes everything in energy. It's a place where stars are born and destroyed in rapid succession, where exotic objects like magnetars, neutron stars with ultra-strong magnetic fields, orbit perilously close to the brink of eternity. The interplay of forces here provides an unparalleled natural laboratory, offering astronomers the chance to witness physics pushed to its breaking point. Yet for all its darkness, Sagittarius A** may also play a role in galactic balance. Some theories suggest that supermassive black holes help to regulate their host galaxies, emitting enough energy during active periods to prevent runaway star formation and recycle material. In this way, the black hole at the center becomes both destroyer and creator, a paradox at the core of the Milky Way. As telescopes become more powerful and algorithms more precise, we are finally beginning to map the turbulent, crowded neighborhood of Sagittarius A** in exquisite detail. The stars that orbit near the black hole, often referred to as the S-star cluster, are like clock hands sweeping through spacetime. Each of their paths is subtly altered by relativistic effects, their orbits precess, their clocks tick more slowly, and their light bends as it climbs out of the warped gravitational well. These motions have allowed scientists not only to confirm the existence of a supermassive black hole, but to test general relativity with unprecedented accuracy, and so far, Einstein's predictions have held firm. Yet there is still much we cannot see. Some simulations suggest that smaller black holes, remnants of ancient stars, may swarm invisibly around Sagittarius A*, forming a dark halo that distorts the motion of stars and gas. These stellar corpses, spiraling in toward the supermassive center, could occasionally collide or merge, sending out gravitational waves rippling across the galaxy. We cannot detect them directly, not yet, but future observatories like LISA, Laser Interferometer Space Antenna, may be able to eavesdrop on these ghostly conversations between dead stars and the dark heart of the Milky Way. And then there's the matter of time itself. Near Sagittarius A*, time moves differently. An observer falling toward the event horizon would, in theory, appear to freeze from an outside perspective, forever suspended at the edge. But for the falling object, time continues normally, until it reaches a place where physics loses all meaning. This duality, where time stretches and bends depending on your point of view, isn't just poetic. It reveals something fundamental about the nature of reality, and how black holes might serve as windows into the very structure of the universe. Some researchers have begun to speculate that the information swallowed by a black hole may not be lost forever, as once thought. The so-called information paradox, one of the greatest unsolved problems in physics, suggests that our understanding of quantum mechanics and gravity may be incomplete. Could Sagittarius A** hold clues to a deeper theory, one that unites the macroscopic laws of general relativity with the microscopic rules of quantum physics? If so, the key may lie not in what we see, but in what remains forever hidden. Meanwhile, the black hole continues its silent reign. It does not glow, it does not move, and yet everything near it responds to its presence. It is a singularity, not only in space, but in mystery. A gravitational monarch ruling a kingdom of stars, whose throne lies buried beneath veils of dust and the whispers of ancient light. It is not merely the center of our galaxy. It is a portal to the edge of human understanding. From Earth, we can never observe Sagittarius A** directly with visible light. The galactic center is obscured by immense clouds of interstellar dust. But with radio, infrared, and X-ray observatories, we can peel back these veils and glimpse the invisible. Instruments like the Very Large Telescope, VLT, the Chandra X-ray Observatory, and the Atacama Large Millimeter/Submillimeter Array, ALMA, all converge their vision on this hidden titan. Their findings are astonishing: a maelstrom of plasma and magnetic fields, a region of gravitational shear and relativistic speeds, and light itself, bent into rings and arcs as it tries to escape. The Event Horizon Telescope's image of Sagittarius A*, released in 2022, was a milestone in this journey. Though blurry, it offered the first direct evidence of the shadow of the black hole, encircled by a glowing halo of hot gas swirling at nearly the speed of light. This shadow is not a simple absence of light, but a gravitational imprint, a signature of spacetime twisted into a vortex. The ring we see isn't the black hole itself, but the last orbit light can make before being swallowed. It is both a boundary and a symbol, a fiery crown for an invisible monarch. And what lies beyond the visible and theoretical borders of Sagittarius A*? Some physicists wonder if black holes like this are connected to the fabric of the wider universe in unexpected ways. Could the center of our galaxy also be the mouth of a wormhole, a conduit to another part of space, or another cosmos entirely? While such ideas remain speculative, they drive a bold frontier of physics where mathematics dares to describe what observation cannot yet confirm. The galactic center is also a crucible of extremes. Temperatures soar to millions of degrees. Gravity is strong enough to twist the orbits of entire star clusters. Particles accelerate to near-light speed in jets and flows, possibly spawning exotic high-energy phenomena. Somewhere within this chaos, dark matter may lurk, shaping the orbits of stars and influencing the motion of gas with its unseen hand. The very environment around Sagittarius A** may be a testing ground for understanding the dark scaffolding that binds the universe together. But beyond science, there is something deeply mythic in this region of space. Ancient civilizations may not have known what lay at the heart of the Milky Way, but they understood that the sky had a center, a place where stars thickened and mysteries dwelled. Today, with all our instruments and equations, we still stand at the edge of that unknowable center. We name it, model it, photograph its shadow, yet it remains a frontier not only of physics, but of wonder. Sagittarius A* is not just the center of our galaxy. It is the anchor point of a billion stars, the invisible axis around which the Milky Way spins. And in a deeper sense, it is a mirror, reflecting the limits of our understanding, the depth of our curiosity, and the immense journey that still lies ahead. As we delve further into the mysteries of Sagittarius A*, we are not just learning about a single black hole, we are uncovering the history, structure, and fate of the Milky Way itself. The stars that orbit near the galactic center are ancient, many of them formed during the galaxy's early epochs. They carry with them the chemical signatures of past generations, encoded like genetic memories in their light. Studying these stars helps astronomers reconstruct the story of our galaxy's formation, its violent mergers, its periods of rapid star birth and quiescence, and the central role the black hole may have played in shaping all of it. In recent years, a remarkable discovery added a new layer to this story, a compact cluster of young, massive stars, the so-called paradox of youth. These stars, known as the S-stars, orbit astonishingly close to Sagittarius A*, in a region where intense gravitational tides should prevent any gas from settling and forming new suns. And yet, here they are, hot, bright, and impossibly close to the abyss. How did they form? Did they migrate inward after forming farther out, or could they have emerged from the wreckage of a larger disrupted system? Their very existence is a cosmic riddle that continues to challenge astrophysical models. Some researchers speculate that the core of the Milky Way may host not just one black hole, but multiple compact objects, perhaps remnants of past collisions, hidden among the glare of stars and gas. Others wonder whether Sagittarius A** will one day become active again, igniting into a quasar that floods the galaxy with radiation. If a large enough gas cloud falls into its grasp, the black hole could awaken from its current slumber, feeding voraciously and reshaping the surrounding environment in a cosmic storm of light and energy. And while such an event might sound distant, its effects could echo far across the galaxy. The radiation from an active Sagittarius A** would not reach Earth directly. We are safely nestled about 26,000 light-years away, but it could impact the broader